Niech ktoś sprawdzi, czy YouTube działa, dobra? Testing 1, 2, 3.
Widać to uderzyło na kąpie.
Widać to? To widać, tak?
Tak.
Dobra.
I ciebie w rogu widać.
Bardzo dobrze. All right. Sorry for 4 minutes delay. So welcome to the 15th Gaia Science Alerts workshop and the ORP time domain workshop, which we held for the second time in this beautiful place at Forth in Crete. So I hope most of you made it here on time, more or less. It's difficult to get. I know we will work it out. Okay, I hope it will not be blinking this way. I would like to ask Vasilis, our kind host, to say a few words. If you could stand here, then people can see you and hear you.
Okay. Hello, everyone. Again, I'm not going to take your time. Really, it's a great pleasure for us that we host the Gaia Alerts workshop for the second time. I think the fact that you are here for the second time means that our organizer with extensive experience actually thought that the previous workshop was acceptable in quality, both scientific and with extracurricular activities. So we look forward to having you in Crete and Forth over the next few days, and I'm sure we'll all enjoy the meeting thanks to the exciting program that was set up. Thanks again.
Thank you, Vasilis. Okay, I'm worried about this monitor blinking. Could someone again check if we are fine on YouTube and Zoom, if everything works, okay? Because it keeps blinking. But let's start with the first talk, and I'll let Milena speak, chair this session. I'm just the technician here now.
Great, so good morning, everyone. The first talk of today and the first talk of the conference will be one delivered by Charlie Gilmore about the status of European Commission support now and future. So, I think the presentation is on already. Maybe if you stand here, it'll be... Thank you.
Yeah. Hello, everybody. Nice to see you all again. And this continued series of these very successful meetings of this program. So I'd like to start with a bit of where it all came from, because there are big changes underway this year, of course. So the first thing to note is that this started off as an OPTICON initiative, as we'll see in a minute, and OPTICON itself started in 2000. And it was the first time there had been coordinated European-wide optical astronomy across distributed facilities. There've been, of course, specialist things like Gemini and ESO. But this was the first time that distributed facilities actually got together. And so it was the first time that many of the facilities had ever met, amazingly. And around 2000 was a special time because new countries were joining ESO. The UK, in fact, just joined ESO that year. ELMA was just approved. But also in 2000, as well as setting up OPTICON, I also presented Gaia for approval to the European Space Agency, and so that started the other half of the sequence. OPTICON was involved in ways of trying to use the resource that was going to become available through Gaia. Although we never promised time-domain astronomy in the proposal for Gaia, and there was quite enough other stuff in there as well. This was a bit of a bonus. And in fact, John Davies, who was for many years the project manager for OPTICON, has written a draft history document we'll put up on websites now, just so that you can correct it and update it of all the things that happened 25 years that we've been now in operation. And so the context at the time was that over the first 5 or 6 years, there was a complete revolution going on in European science. And so, in particular, when the UK joined ESO in 2000, and I became the council representative on ESO Council, and I was allocated the task of negotiating membership of new countries. So that included Spain, as well as small places like Austria and Finland and so on. But Spain then, instead of competing as had been the possibility of having a European Northern Observatory and building up independent structures, independent agencies, all came together. And that took a lot of time and a lot of effort. But the consequence of all these moves into big intergovernmental things is the same as we're seeing in right now, is that the money gets squeezed. So when governments join big international programs, and in this case, Alma is the big new thing, all their budgets have to go into those things. And so it was obvious that the idea of national 2, 3, 4 meter telescopes was going to change. And so we started to plan for that through OPTICON. That was one of the things we were starting to do. And part of the initiative that came from that was our common time allocation system that started in 2010. Also around that time we had the first ever meeting of telescope directors, European telescope directors. They didn't even know each other unless they had to be on the same mountain. And so there was a lot changing and a lot of opportunity to do things differently and better at that time. And I hate this thing. It's too complicated for me. Right. And so things continued over more than a decade, and so the expansion, there was a big expansion of OPTICON in 2013 under FP7, as it was at the time. And this italicized text there that you can read was one of the 5 new initiatives that was coming at the time. So this you see was time domain astronomy, and in particular Gaia alerts, as well as other bits of time domain astronomy. But this was the first attempt Europe-wide to try and coordinate time domain astronomy, and particularly build on the possibility of Europe's own alert stream, which was Gaia. And so that statement from then was the beginning of what's happened now. And the results from this, of course, led to a very bright young postdoc involved in this stuff. And in the exploitation side of it, and another very bright young postdoc who's also in the room working on the Gaia side of it to develop the stream. And so we got going. There was yet another bright young postdoc who just was good at this stuff, right? The Cambridge calibration server, this data processing pipeline system. But then, as is always the way, funding agencies like to do more things than they can afford. So they like, once a project is approved, they like it to focus on its core mission only, and all the added value extras get squeezed. And so the UK Space Agency, which is funding all this work, turned off the alerts work. My colleagues in Cambridge said, right, I'm not allowed to do this anymore. This is the end of Gaia alerts. It's a brilliant piece of imagination. But anyway, we managed to go. So Simon Hodgkin in particular put an awful lot of work into it with a few students, and we kept the whole thing going in spite of a complete absence of formal funding and official support. But it worked, and that's a nice example of how one can do things in this motivated people. Right, so then what comes next? Well, we're getting into the same stage of this. Oh dear. Hang on. What have we got here? Right, okay, we're back where we started. Right. Okay, so the next thing is, of course, there was a lot of other stuff going on at the time. So OPTICON was a big organisation, a big budget, a lot of partners, and it was doing all these other things. And so the idea was to try and learn from all these other projects that OPTICON was starting Some of them were instrumentation for the VLT, so you see those two turned out triumphantly. One was the European Extremely Large Telescope, which I, as well as all this other stuff, I was the first PI for VLT, which has become a big project in its own right, a Gaia scale project, and is on its way to completion. But also we were able to pick up and continue existing programs like the training schools, which had been underway for a very long time under the name of NEON. It's one of those historical pre-ESO names, but all these things were picked up and kept going. And one of the, right at the top there was another interesting new initiative, which is again, whose time is now coming, was the European Interferometry Initiative, which we again sponsored as like the Telescope Directors Forum for European Institutes interested in interferometry. And that's now developed as well as all the technology stuff. Oops, I'm sorry, I'm failing your IQ test. Right, so after 20 years or so, now 25 years, this is our 25th year, the EC-backed support for public access to facilities is ending. And so after OPTICON and then OPTICON-RadioNET, we're in essentially our last year of EC funding. And we know that there will not be a smooth continuation of this project for the first time in a quarter of a century. Also, of course, Gaia is aging, and so the data stream will end on mid-January, and that's the end of data taking. But, of course, the public part of the Gaia data is a tiny part of what Gaia is actually taking. So DR4 and DR5 over the next half a decade will continue and will be enormously valuable resources and time domains and archives for not only discovering things, but also building archives and light curves and determining the astrophysics of all the sources. So all this is still there. The whole thing is continuing. And VH-TOM is continuing as well. There is this new project called ACME, which is multi-messenger astronomy, but it's got a little bit of mainstream astronomy in it, and electromagnetic astronomy, should I say, rather than mainstream. So that's continuing at a low level. So there's a little bit of resource available for the next 4 years, but then not after that. And so in the meantime, your VH-TOM network has grown from just an internal project inside OPTICON to what is actually a virtual distributed infrastructure. But it is in this complicated state is that it is effectively a research project that's grown and become an infrastructure without ever actually being an infrastructure. And so now is the time when one needs to think rather carefully, using our last 3.5 years of available rather limited funding, to say, okay, how can we make this thing viable as a long-term infrastructure rather than as a specific science-motivated research project. And there, the TOM system, Rachel's a good example of how one can make these things viable in the long term and move them to a different scale of time domain astronomy.
I know why, sorry.
I've killed it, haven't
No, it's me. Right, try now?
Yeah. Okay. So, people are thinking we are working on what comes next and how we can make this viable and how we can work in the future. The funding environment is changing. The real structural change is that the EC has completely changed its policy. I think probably illegally it violates its own requirements to support the community. But it is the infrastructure part, which is what we are, of the EC, is now decided to become totally focused on ESFRI, which is a big infrastructure, things like the European Extremely Large Telescope is an ESFRI project. So these are €1 billion plus scale projects. So normal sorts of stuff that normal people use are no longer eligible for any of this stuff because you don't cost €1 billion. And unfortunately, the EC has also delegated policy and strategy to Esri, which is far from expert in distributed infrastructures. And so there's been this inversion of the way that the EC gets its advice. It used to be a bottom-up, community-driven leadership, and so every year for most of the last 25 years, the EC would invite all the project coordinators over to Brussels for a day or two, talk to us, say, what do you guys need, how are we going to do this, and try and deliver what the community actually wanted. Now, there was a change 2 years ago where all of the top-level people in the EC infrastructure division all retired and all replaced by professional bureaucrats. So that we're now run by lawyers and people like that, rather than people who actually 3 of the top 6 people had PhDs in astronomy. And that's why they understood what we were doing. They understood but that's now different. They're now Luxembourg lawyers, and they don't know what to do, so they've outsourced the decisions to the organisation that they were talking to, which is, of course, not interested in anything that costs less than €1 billion. And so we're in this difficult situation. There's a further complication, is that Opticon was not the only organisation in astronomy. There's many people who chemistry, databases, planetary science, all sorts of things. And all these other people have also been squeezed. And so there's a very considerable pressure on essentially no money right now. And so we need to be more imaginative. And so we will be, and we are, but that's not yet not a solved problem. So we need to think of new ways of getting resource to ensure that there is a future more than 2 or 3 years from now. Now, just very briefly, this is what we created. Of course, the CTAC is what it is right now. There's a list of all the telescopes there. It's everything from really big things like SOLT down to little stuff like REM and the Las Cumbres smaller telescopes and so on, plus, of course, PH-TOM, which is all partly in this TNA, as it's called, Transnational Access. It's all over the globe. And the process has been very straightforward. Same process as the EM-TOM. It's totally open. That was the whole thing. There was no eligibility requirement whatsoever. The only requirement is that you were able to write a competitive proposal and that you were a big multinational. So you couldn't just ask for competitive proposals on your own facilities and expect the EC to pay for it. But other than that, it was hugely successful. And in fact, it was such a success that after it got going, the EC was using this as a role model for other communities who were trying to come together. So the atmospheric chemists were told, you should go copy the astronomers. Why report a pilot? They were also a pilot. They'll go and talk to these people and learn how to do it. So that was very successful, very popular at the time, but it's now come to an end. And again, just to remind you that there's more to access than just using data. You can also do experimental access. So this is another of the programs that grew under Opticon. So it was access to experimental facilities. And so this is something that's worth bearing in mind, is that one needs to keep a broad view of what is access to a telescope. You don't necessarily just want to look at some astronomical source. You might want to develop instrumentation. But this is another thing that's coming to the end of its current life, and so we'll have to try and think of a new future for it. Because the William Herschel telescope's now not available to weave. However, there's other big changes going on that we have not yet come to and will be in the short term, things that dominate this community and others. And that is for structural changes in the way that small telescopes and survey telescopes are operated. So the first, just as an example, there were these 4 1-metre telescopes at Tololo. They were called SMARTS. One thing they're good at is acronyms. And so instead of now being part of a community pool, they've been offloaded to 2 different university groups who pick up 2 of them each, but using them as private projects. So they're no longer public access facilities. So 2 of them, for example, Georgia State has picked up the 2 middle-sized ones and has running a program on active low-mass stars. So the telescopes themselves have been essentially donated just to keep them going. So there's another possibility. And there's again exactly a parallel analogous with what is happening with the inertial telescope. Telescopes are becoming special purpose rather than general purpose, because general purpose is expensive. The other thing that's happening, of course, is the alert follow-up systems. And there is a very large number of these things already in operation coming on stream. I mentioned just two there, there's BlackGem and GoTo. And there's a picture of GoTo. This exists, it's in operation. And it's this new concept, you cover a very, very wide area of sky by having a lot of small telescopes that are piggybacked on the same mount. And so this thing is imaging huge areas of sky continually. And the data are there. What do you do with it? So the focus of many of these things, of course, is that they look for a transient. So the go-to is a gravitational wave observatory follow-up. It's mad. But of course, the number of optical electromagnetic gravitational wave events is 1 per decade current success rates. So for most of the time, it's not doing that. So what's happening to those data? You know, there's light curves for hundreds of millions of sources being detected every night by all these things. And why are we trying to compete with it? What are we going to do with it? So this is a huge future challenge, is how to get involved in these archives. And in fact, the style of wide field, rapid follow-up things is expanding rapidly. There's one even being built up here on Skinnicus as a joint local and US thing. And again, it's one of these multiple small telescope covering a very wide field, 100 square degrees per snap. Now, somewhere in there might be a transient gamma ray burst or whatever that you're interested in. But there's an awful lot of other stuff as well. So we need to come to terms with how to access these totally prodigious archives. And the next generation of these things will produce tens of petabytes a night per facility. And this is not something that we know how to manage. It's even a challenge just to produce a handful of transients of interest out of a thing like that. But of course, that's less than 1 millionth of 1% of the data. So it's not an intelligent way to run a facility. You sort of throw away 1 part, or except 1 part 10 to the 8 of what you've got. It's not just noise, it's signal. So anyway, the next generation, and we don't know how to manage this, is how to do more than just find extreme transients and stick them into brokers and have a handful of follow-up things. And so this is the challenge that we now have. It's not a question of just continuing what we're doing. There's been a complete revolution in the last couple of years, and there's an even bigger revolution coming in the next couple of years, which is just going to swamp everything. And so you have to say, well, what's the point? What's the point of building an LSST if we've already got all this stuff? And so it's a very interesting intellectual challenge that we all have, is that the time scale for building big infrastructures like LSST is so long that the entire community has changed completely by the time they come on the stream. So we haven't been keeping up to date with what's really going on. And so, well, we're all going to go through an interesting learning curve, but I suspect that there's just going to be vast quantities of wasted money producing stuff that no one ever looks at if they're not very careful. It's not intelligent and doesn't make a good case for our future. Anyway, what we need is money, of course. So what's happening now, of course, is where are we? Well, we don't know, is the odd thing. As part of this concept of buying in professional, highly made, highly paid, experienced bureaucrats to run things that nothing works. And in fact, it's true in this case as well with the EC, so they're a year late with their net planning. So we haven't got a plan for what's going to happen in January yet. The EC hasn't announced it, and they're not going to announce it until January, because they're no longer able to plan a year ahead the way they always used to. So again, this is a concept we have to live with. We have no idea what is going to happen in the next 2 years. It's not been decided yet. There are rumours. The rumours are that there's not going to be anything for astronomy. So there may or may not be something a year after that, which will start a year after that. So we have a plan for in our funding. And we have to try, and the competition's got worse because this backlog was built up. There's also restrictions. The EC has decided to adopt this brilliant UK system of deciding exactly how much money you need to do a project and giving you only 80% of it. So if you're really serious or rely on your application by padding it up by the extra 20% because you know it's going to get cut off or whatever. But anyway, these are the new systems in which we have to try and be creative and look for new ways of doing things. And there are ways of doing things, it's just they're not going to be through our traditional research infrastructure way. That's not our future. There's no point in expecting it will be. We need to be more intelligent. And so what next? Well, these are the things we need to do. In the short term, of course, there's not only the new archives that are just about to start generating stuff. They've got no history. But there are an awful lot of archives out there in the existing observatories. So our existing 1 to 4 metre telescopes have been in operation for decades. Most of them have absolute rubbish archives that you cannot get at in real time. So if you're doing transient alert on a timescale of milliseconds, there's no point in sending an email to someone and asking them to look in their archive because it just doesn't work. Okay? So that's a short-term challenge, and ATME may be able to help with at least the easiest test cases of those. But there's an enormous wasted resource in the historical literature. The same mistake that we're about to make again is you just acquire data and never look at it. It's just frankly silly. But anyway. But in the meantime, the challenge for the VH-TOM community is how to turn it into something that's recognised as a distributed infrastructure. And that's not an easy challenge. But there's no possibility of funding a single research project in the long term. There is no precedent for doing such a thing because the scientific interest changes. And so the community has no future unless it's presenting itself as a more broadly focused time domain astronomy research project with lots and lots of science cases. And so that has to be done. And then in the longer term, and this is what we will be doing leading from here and forth, is looking at other funding sources, so going away from the traditional infrastructure stuff to other ways of raising money. And here's again where we could perhaps learn from the very different US model of private-public funding, which has huge challenges of continuity, but huge opportunities for large amounts of money. Donors. And these people exist in Europe as well, but they don't fund science, but we'll work on that. So that all of this, however, needs change. The famous phrase is, if you want things to stay the same, then you have to change. I think that's a part of that was first from, but it's a ubiquitous statement. Is that my last slide? I can't tell this crazy thing. Okay, so, right, I'll stop there. Thank you.
Thank you very much. Do we have any questions or comments, suggestions?
Comments on the European Commission. So my impression of the European Commission is there are few people in the European Commission who are extremely good. There are others who only work for their CV. So they look at their key performance indicators and see that they make a good career, they're not interested in what they're doing. And there are lots of branches within the European Commission and they never talk to each other.
A very good point, Martin. Yeah, I think you're very perceptive.
I have a question. So, in the next year, in upcoming years, there's going to be several other surveys, Spider-Man surveys starting. Is there any plan to try to convince the funding agencies, touching OPTICON or the follow-up OPTICON
Yeah, we started trying to do that. It comes back to this repeat of what happened when everyone, the big countries in Europe joined ESO, they said, well, you know what we are things, and we don't need forming ourselves, so we've got to be ourselves. So the default reaction is that, well, we're paying all this new stuff. Your old stuff, your problem. So we have to still go through that educational process. So that everything complementary and make it clear what is unique to what different scale of operation and what different cost model. And that isn't understood. I think it was likely at charts and there's a whole generation of people who were all individuals who came in at around the same time, 25 years ago, when we started this at the time of one. And we're all getting to retirement age.
Yes.
So there's a whole new generation of people coming in. They're coming in and seeing only the mega structures. So they don't realize these things grew and things. And we're in the whole flying range here. You're right.
I mean, 4-meter telescopes would be perfect for us to still follow up, just saying.
Right.
It's like,
Yeah,
no other telescope can do that. Like,
I mean, one of the pretty obvious things from all this stuff is that we've got a system generating literally hundreds of millions of light waves at a time.
yeah, true.
So there are a few very obvious elements, but we need to have to make that case. Because people don't know.
Thank you very much. You?
My favorite device. How does this now?
So it works like a go right, and
Yep.
the laser is inside.
Okay.
Just a general comment, and it would be great if we could speak a bit louder because we have some people joining us on Zoom, and we have so now we have a microphone working from the laptop, and so that's like it'd be nice if we ask questions, especially if we ask questions, to try to make it a bit louder because like from here it's fine. Okay.
Okay.
Simon Hodgkin is now going to tell us about the decade of Gaia Science Alerts.
Okay, thanks very much. Thanks so much for having me. And it's great to be here. I've never been to Crete before in Heraklion, so it's very exciting to finally be here. So I'll try and give a quick whiz through. I know this is probably new to some people, but probably very old and they've seen it many, many times. I can't believe it's almost 10 years and I feel a bit emotional that we have less than 4 months to go of operating this system. But as Jerry pointed out, DR4, when it comes out, will have per epoch measurements of everything you've ever seen until 2020, so the first 5 years, so half the Gaia mission will be in DR4. So you can go and find all the things we missed, which I think will be plenty of things, because it's quite stressful and hard to do it in real time, whereas the astrometry and photometry is so much better in DR4. And then DR5, the same again, another 5 years. It's going to be incredibly rich, so there's plenty more transient science to come from Gaia, even if we stop running the daily operation. So a lot of this stuff is in this paper, and I'll come on to that. So just a reminder that trying to do a transient survey from catalog data with no pixels is really hard. So we rely on the onboard algorithms, and we rely on the initial data treatment that happens in Madrid, and they do a very good job. But the sky can look like this to us. These are the catalogs of sources that we ingest every day. And then we have to work out which source belongs to which. That happens for us, but it's not always correct. And sometimes there's a magnitude term, such that if a source got brightened, it got given a new source, a new classification, even though it's an old source that brightened. So the sky looking like this is a headache for us, and it's made the first year and a half of Gaia Alerts very stressful, but then we learned a lot, and we had very clever people who managed to solve most of these problems and end up with quite a stable operating system for the last 10 years. And reminder that we basically have two classes of source. We have sources that are new on the sky to Gaia, or we have sources that we've seen before, but they change significantly in brightness. And we allow things that either brighten or dim. So both those classes are interesting to us. And the kind of idea here is we have 10 to the 8 transits, measurements per day, that we ingest into a massive database, and it just
swells and swells and swells. And what we have to do essentially is work out, well, which of those transits are robust measurements and which ones are dodgy. And then we run a detector on the light curve to look for things that can do this dimming or brightening or be new to Gaia. And our brightening can be quite subtle as well. We can look for things that change slowly as well as look for things that change suddenly. Then we try a fairly sort of basic classification to get of order thousands of candidate things that we believe are true events, alerts. And then we run filtering on those to get rid of a lot of them, which we decide are environmental, actually, and not true alerts. And we're left with tens of things that we look at. We always wanted to do this with machine learning algorithm. We did invest. People did a lot of hard work on it. And in the end, when they kind of pulled the plug out of the funding, then that had to come to an end. I didn't trust it at that point. I kind of felt like, no, we'll carry on with the unpaid humans. We'll carry on doing it. So thank you, eyeballers, for all your hard work over the years. And we end up of order 10 per day of things that we discover. So these are the scale of these different orders of magnitude. So we have 10 to the 8, plus or minus. That's an order of magnitude variation, number of transits we see per day. And those spikes are when we scan parallel to the galactic plane. And then the number of things that the alert pipe system detects is down at the thousands or possibly tens of thousands of events. And then we do this environmental analysis, which is quite challenging, and then we end up with tens of events that we eyeball, which is the red curve, and then the solid black line at the bottom are the number of things that we actually publish to the community, to the world. And the environmental filters we have to apply take up 60% of the mitigation of rubbish. And these are wings of a bright star, or you're near a planet, or you're near a neighbor. So even being close to a neighbor, even if it's quite a faint neighbor, can cause problems when the window lines up with the neighbor. You get an excess of products. But we also filter out known solar system objects. We have very precise tables, especially over the year, got better and better. And Francois Mignard would send us a list of predicted transits of known solar system objects. We have known variable stars, so we mitigate against those if they're uninteresting classes, and we also mitigate things that are high amplitude red, historically probably Myra-like objects. It doesn't work 100% well, but it gets rid of a lot of the stuff so we don't have to eyeball as much. And these are the kind of images we use for eyeballing. So we have essentially, we have a series of things that show us the position of today's transits that did something exciting compared to historical measurements of the source. We can see the neighbors of the source. We can see the light curve of the source, the historical BPRP, the color of a source. We can see the goodness of fit of the PSF of the source. And so we have all these parameters that help us decide if something is real or bogus. And then we look at the environment. So if something passes that, for the eyeballers, they can also look at where is it on the sky? Is it near a galaxy? Is it not? And they can look at the BPRP spectra as well and see if there are any signs of emission lines or this color. And so all that information is given to eyeballers. And we got very skilled, and you can do it in less than a minute per event. Just go through them. So if you've only got 10 to look at, it's fine. It's a 10-minute job once a day. It's quite a lot of fun, which I will miss. The important thing with Gaia is the cadence is quite low, and even though it's the most precise experiment you can imagine, I wouldn't mind if it went a little bit quicker and more frequently, because everything looks a bit like these solid blue dots. It just gets a bit brighter then a bit fainter. What's that? Is that an M-dwarf there? It could be anything. But it's only thanks to you guys going to do the follow-up that you can make discovery. Otherwise, the whole sky looks like this. It's only when you go and follow these things with these little points, which are you lot, doing photometric, precise, high cadence follow-up, that we can see actually this is a cosmic crossing event and this is binary microwaves. So that's where the discovery space lies. So any fool, me, can find transients, but knowing what they are is the key here. And that's never going to change. As we get LSST land, this is going to get a worse problem. So we have to think about that. And these are just a few of my favorites because I can. So this is an outbursting event that we discovered with Gaia, which is the bottom light curve in blue. And then Lynn Hillenbrand and team
wrote to us and said, is that interesting? I said, I think it's interesting. So she went back and looked in the WISE photometry and saw that it brightened a year earlier in WISE, and classified it, they got spectroscopy, and classified it as an FU Orionis event that happened from the outside of the disk in. So this told us suddenly a lot of physics about FU Orionis events that hadn't been seen before. And so again, this is sort of serendipitous science that came out of just finding a thing that got brighter. That's quite a lot brighter. That's almost 3 magnitudes brighter. So it's a significant event. Discovered in the optical, but understood better thanks to combining resources from other missions. And this is a paper that I really, really like. So this is Adam Kawash, who was here, I think, 2 years ago. Or anyway, he came to a previous meeting and presented this work. And this is measuring the galactic nova rate. And in Gaia, in this year, which I think is 2021, they're the largest number of galactic novae ever detected. And more than half of them came from Gaia. So Gaia is a very effective galactic nova discovery machine, and still continues to be. And so there was they were able to go and measure the galactic nova rate in our own galaxy, which is quite hard to do. It's easier to do M31 in a way than it is to do our own galaxy, which seems absurd, but that's the case. And so there's a nice paper from Adam where they go and investigate and measure the galactic nova rate. So this is where we are. This is 26,000 and a bit published alerts as of Friday. There's about 50 more over the weekend, which are arriving to your inbox, Łukasz, and there's some really nice microlensing events that you want to go and start following up, and one of them is pretty bright. And our classification rate has remained at about 30%. You can see there are occasional flat plateaus. There's one I've highlighted in blue, and this is where we have issues. So because we stopped being funded, we're stuck with a database that was too big and no new resources to replace the hardware. And so we're like, what do? We need to keep running this. We don't want it to die. So we kind of took half the database and partitioned it off, and then just tried to forget about it, and then work with the other half of the database. And then only if something interesting happened recently, then we go and extract the old measurements to use them. So this helped and meant we could carry on operating, because basically a year ago I thought, that's it, this is no longer going to survive. And luckily the few brains we have in Cambridge are quite clever, some of them, and they were able to solve this problem. So we keep running and we can keep going to the end of the mission now. We also learned doing backups before you do operations in databases is crucial, and I'm very glad we did, because we lost it and then we got it back. So look after your databases, they're precious. The precision of the photometry is 1% at the bright end, and then it gets a bit funny when it starts to get a bit bright, because the initial treatment of the photometry is not that great. It needs the iterative cyclical processing that we can't afford to do. And then at the faint end is about 3%. And this is a precision, not accuracy. We have tied it into other systems, and it's pretty good. But there's a caveat here. The last time we updated our photometric calibration was 3 years ago. However, the light curves of everything we look at and publish still looks flat, which tells us that Gaia has been an incredibly stable instrument. The reason the calibration hasn't been updated is because the team doing the photometric processing were responsible for giving us the calibration. They're much too busy right now. It's a really stressful time. So we give them breathing space, and we can live like this. This is okay. Aha. And the astrometry is really good, and has become ground truth for all transients detected in the sky that we see as well. Our astrometry is where the thing really is, compared to other measurements from the ground, which tend not to be so accurate. So that's a lot of experiments done by the TNS group to demonstrate the precision of the Gaia, accuracy, sorry, of the Gaia astrometry. And then in terms of classification, so about a third we classify, and we're dominated by supernovae. Most of the things that we classify are 60% are supernovae. This is because people love supernovae, and they go and classify everything that can be a supernovae. And they're not all only discovered by us, they're discovered by other surveys as well. So they get really good data now. And they go and classify them
like crazy. But that's not, most of the sources are not classified. 70% we don't know what they are. So there's something to think about there. And if you look at the whole sky, our transients are the whole sky. Assassin is the only other one that really goes whole sky. And we can go in the plane, whereas these other example surveys avoid the plane, like it's an uncomfortable place to be. And so when we look at classified versus unclassified, then there's this incredible bias that if you're in the plane, forget about it. No one's going to look at you or care about you. You're just not going to be well loved, except by some of the people in this room. But everybody else is driven towards high galactic latitude. This is a nice figure that shows the evolution of a number of transients that we published just to show where they live. And so we could, in theory, build beautiful machine learning algorithms to classify everything on the fly and do a really good job. But that needs resources and funding, and no one's ever done it, sadly. But that would be the kind of thing, if I could do it again, and I could hire some people, I would have done that. So we've shown it's possible, demonstrated it, but it never really got picked up, and yeah, they pulled the rug firm under us. Unfortunate moment. And this is showing the same image in another way. It's just that you can do a simple classifier between young stars and CVs. This was done in a paper and led by Thomas Wavers as part of the analysis, which is nice, very simplistic, but shows you can do this quite robustly, reliably, at least for these two classes. And then Mystery et al. Extended it to a larger set of classes. I think there were 5 classes of it all in the paper. Very similar approach, but they included AGN, QSOs, that class, kind of classes of sources as well as supernovae. And so it's possible, it's doable, but we were never able to turn this into a real-time thing that we could do at the point of publication, which would have been very helpful for the community. So it's a shame. So I'm going to kind of start heading towards the end. I did an exercise just the other day, which is to look at the number of publications that cited the paper we published in 21. So the blue ones are the differential histogram of those, and the black ones are cumulative. So so far, it's been kind of growing slowly. We'll have to see what happens the second half of 2025. But it's quite a reasonably productive survey. I know that this is an underestimate, and there are many papers that acknowledge us but didn't cite us. And also, because I was kind of late getting the paper out, there's probably quite a few who would have been citing us if I'd been quicker. So apologies for missing citations for my co-authors. And then this is the breakdown of what they were talking about. This is the thematic distribution, which I've deliberately unlabeled. So audience participation, what do you imagine the largest 3, and just generally throw it out there, the largest 3 things that people are writing about Gaia alerts are? Do I hear any suggestions? Supernovae? Microlensing? Novae? AGNs? I'm not hearing the biggest one, weirdly. No? Yes, we have a winner. So the largest ones, by far, well, not by far, but significantly, are the young stellar objects. Then supernovae, yeah, spot on, and then microlensing, we had a microlensing right there. TD, I'm afraid anything that had the word TD somewhere in the paper, I put in the TDE bin, which doesn't mean, you know, there's a lot of controversy. So, which is maybe why AGN looks so small compared to TDs. So, not looking at Michelle. And Novi, yeah, there's been a couple. So it's quite interesting. There have been some searches for extraterrestrial life. There have been all sorts of things citing our work on alerts, which is quite interesting, the diversity of works, and also some looking at methodologies and surveys and things. So it's got quite a nice diversity. I'm probably running out of time. Did I miss one? Yeah. Okay, so last few points. Gaia X has been running for 4 years now, 4.5 years now. It's still running.
And this is a single field of view, so it's a noisier transient stream. We don't do this requirement of seeing it twice. Once is enough. It goes all the way to the limit of Gaia, more or less. We have to put in a lot of extra filtering, so we miss the plane, the bulge for these things. But the idea is to get things that could be coincident with gravitational waving events. And so to do that, you just need to get it out fast, and you need to, as long as you know where it is and when it was, that's probably enough for a gravitational wave event with this other surveys joining in the mix. So these are published, and so we did some preliminary work to try and understand, were they real, or are these just artifacts of Gaia? And that was led by Sumedha Viswas. And we will be doing new tests. I'm in the middle of, I thought I would have it ready by today, but I don't, sadly. It's still going on. Using ZTF for a larger sample of objects to try and understand better the distribution of things that we find that they see. We will keep running until January. That will be the end of the alert stream, so don't be applying for Gaia alerts follow-up after January. And then DR4 and DR5, you will still be able to go and understand what the transient sky looks like, even though you're not catching them in the act. So it's like the paper you did for CU7, Wukash, you can still find all these microlensing events, and I expect much, much more of that kind of work to come. So I'll summarize, I'll wrap up. You've all been doing amazing science with the alerts that we've been publishing. So thank you for your hard work, and everybody else in the community is really hard work. We're over 26,000 at, I say 10 per day, but if you divide the number of days of operation by 26,000, it's not really quite 10 per day. But when we were running smoothly, it's 10 per day. The astrometry is accurate. The photometry is good enough, nowhere near as good as the Gaia data releases. We're one of the few transient surveys that can go into the plane, and definitely the deepest of those. We classify only 30% of the alerts. That's still okay, and probably better than many surveys, and much better than surveys like LSST will do. That will be a struggle there. But I think we can do much better, and I think we've been shown by a couple of papers how to do better, and it's a shame we didn't implement it, but we still can, retrospectively. And Gaia X could still, in the last 4 months, give us something. So I'll stop there. Thank you for your time. Thank you for the water.
Thank you, Simon. Any questions? Yeah, please. Sure.
So, two things. Firstly, thank you for running this system. As someone who runs a follow-up project, our science depends on what we've done, and your team have done a tremendous job. So that was point one. The second point about the classification of the alerts is, have you spoken with any of the alert brokers that have been developed for LSST? It could be a really useful test product for them.
Yeah, I feel a bit sad that we didn't get a better interaction with some of the alert brokers, because they could have been ingesting us, and we were public, and nobody did. And I feel that's a bit on me to not have gone to encourage them more to read our data, which is a shame. So as far as I know, none of these Mars, Antares have been sucking us in. The only one that has is TNS, and everything we've ever published went through TNS. And so it's been there, but I guess people love their supernovae.
They do,
Yeah,
but I feel like there's a potential collaboration there, even if it's Gaia's ceasing to observe. I feel like there's a useful case that they can do there. There's a huge amount of development that's gone into it.
Yep, and I completely agree, and I would love to talk more about it, and maybe we can,
Yeah, let's do that.
All right, thank you.
Just follow up.
Oh, I just have a follow-up for that. I mean, it would be good to just provide a classified set of classified, like labeled transients from Gaia Science Alert with the time and detection. And I think that would be a very good thing for brokers to have to like test the algorithms and maybe refine them.
So we do that. We publish our
Yes.
alerts and our classifications.
Yes, but I'm not sure if they know about this.
Well,
So it's worth reaching out.
they kind of, yeah.
Sorry.
No. I think you're right, and I don't know how to tell them that if we can get together and come up with a good project. You're also OGT now, right? Yes,
Yeah.
good.
I'm also
Then we
working
talk.
with Black Gem.
Then we talk some more. Yes, please. Thank you.
Thank you very much.
Thank
you,
you.
Simon.
Thank you.
Thanks to Gaia Science Alerts. And now moving smoothly to Łukasz Wyżykowski, who's going to tell us about the BHTOM global network of telescope and research infrastructure for time domain astronomy.
Thank you, Milena. Perfect pronunciation of my surname.
That was
I appreciate that. So just to add a comment to Simon's talk, so Simon forgot to mention that it's actually this month we celebrate the 10th anniversary of the first Gaia alert, which was, if people remember, it was supernova 1A. What else could that have been? And it was named Gaia 14AAA, right? So that was fun. It was quite exciting times to announce this. Okay, so I'm going to move to the BHTOM telescope network, and I will just start with the map of telescopes involved in that. And it was mentioned a couple of times that the alerting system was in place. We put it in place already. It started operation in 2014, but we were working on it many years ahead, right? Even before Gaia was launched. So while working on this in Cambridge, we thought that what's the point of alerting if the science is not going to be made out of it? So in parallel, we started designing this network, and to our surprise, we found that there is many telescopes which are smallish in diameter, but still they are interested in getting involved. And some of them were just sitting there waiting, tell us what to do, right? We are there, we have plenty of observing time. We can contribute, we can observe these much more frequently than Gaia has. And Gaia 16A/E was one of the first highlights of that collaboration. Okay. I will show some faces of people involved in that particular part of the job. These are mostly people from Warsaw University Astronomical Observatory, where we mostly operate now. After I moved from Cambridge to Warsaw, so there is some staff people, postdocs, students, former students like Katarzyna and Chris. Yes, and we collaborate with universities of Toruń in Poland and Heidelberg, Lithuania and Vilnius University, Slovenia, and then many other institutes and collaborations. You see these people carry some tags. Some of them have Gaia tags, means that they are involved in the Gaia data processing. So you could see on the eyeballing chart of Simon, some of them, like Chris, Katarzyna, Nada, they were contributing to the eyeballing system as well. Some of them carry the ORP logo. So these are people who are currently funded through the OPTICON-RadioNET pilot, which finishes actually fairly soon, in a couple of months. There are some other labels. You can read that. So that's a busy plot. But anyway, this is the current status of our group and people involved in all this work. So I show this typically at the very end of my talks, but here I start with this to say that when we were thinking about Gaia alerts, we realized that we need to let people know about it. We thought back in 2010 in Cambridge that we should have a meeting and get people over to essentially learn about what Gaia is going to deliver, and also to get organized about the follow-up. So we are now here, right? This is the 15th. So you see, I need to completely redesign this slide because I ran out of space. Because we've been running these workshops essentially through every year, even through the online times, let's say, in various places around the world. So let's get back to 2010. So this is the picture of some of you there, young and handsome. So I think many of people who are at this picture, they're still collaborating with us. So this was held in Cambridge, and this is the agenda we had. Unfortunately, I didn't back up the slides. I need to dig them out somewhere. I have them somewhere, but I couldn't get to them easily, actually. But this is the agenda. You see the speakers and the topics here. So we were talking about Gaia, what Gaia is going to be, right? We have Timo Prusti, who's just recently stepped down from a mission scientist. And then we had science alerts talks by Simon. We were talking to asteroid people. And then we had a review of what is the current state of the transient world. And following the question of speaking with the brokers, I think when we were starting this, no one has ever thought about that. I think we were kind of pioneering the thing here. It wasn't new, but we were still pioneering the large volume of data streams. And people were not ready for that yet. That's my feeling. Only later with ZTF in particular on the US side, things started to kick in, right? But here, the landscape was very, very different back then. But there were some transient surveys ongoing. You see there is PTF was running at the time. There was Catalina. Assassin was about, well, it was still in planning. It wasn't there yet. And then we covered a couple of science cases just to get the feeling on the landscape. But also what we did back then, with Simon and contributions from many other people, we wrote a white book, right? Many people do this these days still, but we did that back in 2010 with a lot of contributions from multiple people. And it actually covers, things we discussed, like what Gaia is, what Gaia Science Alerts is, and how are we going to approach this. And then the last chapter, challenges, actually I picked one section there on the follow-up observations. We discussed that in this white paper, because we had a lot of very interesting discussions with people there. So we talked about the resources, we talked about who is interested in the follow-up, right? So significant interest was expressed from supernova, microlensing, and CV communities. So actually you can see that in Simon's plot. Well, maybe YSOs were not there yet. But still, this turned out to be the most active communities over these last 15 years. But then the last plot I emphasize here is who is planning to coordinate follow-up of the Gaia Science Alerts data stream? What aspects of Gaia Science Alerts most interest these individuals? So at the moment, no coordination of the follow-up has been planned or discussed. It's discussed. In fact, to be clear, it is not something that DPAC, so the Gaia Consortium, will coordinate, right? So the Gaia Science Alert stream was from the very beginning, it was planned to be public to the world. So this is the responsibility of various scientific communities to coordinate any such activity themselves. And then we planned a science verification, however, within DPAC, we received a letter of intent from Gaia Variable Stars team to help with this process. We plan to organize coordinate follow-up during Gaia cycle 0, so from the very beginning of Gaia. So this is our kind of conclusion of that meeting, that we need to coordinate ourselves, right? So that is not going to be something done by the Gaia consortium itself, because Gaia has already a lot on its plate. So actually that kicked out all the activities. That's why we are actually here. And so we started doing things. So the network of people interested in the follow-up was established. And then the very first tool we built with support from Opticon was called Cambridge Photometric Calibration Server. This is the name we call CPCS. We started in 2013. So we developed this in Cambridge with a clever postdoc, Sergei Posov. So as the input, because we had already this network of heterogeneous telescopes, right? So we need to make sure the data we get out is standardized in a common way. So this is the tool we devised. So there was an input photometry coming from any kind of telescopes. And then we standardized this photometry for selected targets we were interested. And then we could produce these nice standardized light curves where you don't see the differences between various telescopes. And we observed something like 3,000 targets. There were at least 10 papers published just using that data. Not only microlensing, just to be sure. Then as a transition, I will point out to this paper, wrote by Paweł Zieliński. Yes. with contributions from Przemek and others. So we started to think that what is missing is actually people struggle processing their data, their images in time, right? Many people collect the data, they wait half a year, and then they come to us, oh look, this is 1,000 images I took. What do I do with that? So we thought that, especially for the transients, but also for any kind of time domain targets, you need to have your data as fresh as possible, right? Ideally, soon after the image was taken. And I come from the OGL project where this was implemented, so I could see this is possible, right? So we wanted to help people to facilitate that the original images, raw images, were actually processed by us. And so Zbigniew Kołaczkowski, who unfortunately passed away too early, with Przemek Mikołajczyk, they devised something what we call CCD FOT. So here in this paper, we actually discussed the prospect of how to proceed with that implementation of that software, which can be automatized and can work on heterogeneous data. So this brought us to PHTOM1, and the Tom name in this name comes from the fact that I was fortunate to meet Rachel. I've known Rachel for a long time, but I've met Rachel in that aspect at LCO, where these people like Lindy, Joey, and others, they have devised this open source Tom system. So I thought, when I saw this, I thought, this is what we need, actually. And it's done by these clever people, so I don't need to do it myself. So we've wrapped everything we've had so far into this infrastructure of Tom. So in practice, it started in 2010. We had something like 200 users registered, 87 observatories. We processed about 100,000 images, and we had more than 1 million data points stored in that archive. And we studied some like 300 targets. However, this system was extremely inefficient because of, I think, of the heavy use of this and a lot of data to be processed. So we had to delete that one and start a new one, which we currently use, and it's called PHTOM2. This is the web address, if you don't know it yet, phtom.space, easy to remember, and the BHTOM, the Tom comes from the name of the Tom, and BH stands for black hole, so that is easy to remember, right? So this is kind of a summary slide I always show here. So this is a web tool for coordination for time domain observations. And it has automated observations request, and then it processes the raw images from heterogeneous units. So you see where we started, and this is now embedded into this system. And it does the automated standardization now, so it has the CPCS in its original form is actually stored inside of this system. It also queries all the archival multi-wavelength time domain photometry. And it's always open to new users, new telescopes, new targets. We can observe any target which is interesting from the point of view of time domain. So just to show the data flow, this is the landscape of the surveys, right? So Gaia is one of them. And then there's ZDF, OGL, Assassin, LSST is going to be in place, Black Gem. You can think of many surveys which are producing loads of alerts, right? These alerts these days, they go to brokers, and I just listed a couple of them here. And so this is where users come in. They use brokers to go through the alerts released by these surveys, and then select targets of interests. If I'm interested in microlensing events, then I check what kind of microlensing events were found by Gaia, and I will be happy to include the new one found by Gaia Alerts just yesterday. But if you're interested in supernovae, then you can filter and find your favorite supernova, and then what do you do with that? Then you come to us, and you say, okay, well, this is not a supernova example, then you found 10 candidates for gravitational wave follow-up, right? So you used some tools to filter through, and then you ended up with 10 candidates. You want to observe them right now, right? But there are some other people who are interested in observing Gaia 20 FNR for 1 year, right? You would never find any TAC who would give you time, use this telescope for 1 year for one target, right? It's impossible. So this is why we designed this. So these observing requests, They are then sent to PhDOM, and we take care of the rest, right? So we communicate with the network of telescopes. We even include radio telescopes in that. So these are the various telescopes we are in contact with. Then we query the data archives for you. You don't have to do that. Some people are sometimes not aware of some of data existing. You see papers published solely on one particular data set, whereas they could have used some other archival data and their science would benefit from that. So we do that for you. And then all this data combined, so the data from telescopes, which is then processed, standardized, and then it's combined with the archives, this is then transmitted back to the users. And the users are in charge of writing the papers. And sometimes they include also all of us. That's the goal. However, where we are aiming at, and actually the system is designed in a way that this can be replaced by bots. So you don't have to have humans in the loop at all. This is where we're heading, right? So we'll be just sitting on the beach in Crete, and then our papers will be written by the bots. But the main thing is that it's not there yet, of course. There's many humans in the loop, but this system is designed in a way that it's how do they say, with the projectors, they were saying it's HD or 4K ready, right? So we are bot ready. So it is there. So hence this is the network. At the moment we have slightly more than 100 telescopes which are registered, and they come in sizes from 0.25 to 2.5 meter. Many of them are run by professionals, but there are also amateur observers who are very actively involved. We have telescopes which are run by schools and outreach facilities. Many of them are run manually, but there are some which are robotic, and more telescopes are actually getting roboticized. Some of them are in good weather, as you can see. Some places have very good weather. Some of them have poor weather. It doesn't matter, because there is actually way more telescopes in poor weather sites than the ones in good weather sites. So they are a huge resource. Many of these people actually, they are volunteering their observing time, this is how we actually based our observations. So essentially, if you have any spare time, any 10 minutes in your busy schedule over the night, you can take one target from us, and then you're already contributing. If we have many more telescopes like this, you can imagine what a resource it becomes. Some of them we access via proposals, and so we have some guaranteed time which we ask for. This is a zoom in on Europe. You see we have telescopes in places like London, for example, a very nice telescope providing very nice data. Lithuania, not many clear nights, but still the data they deliver, it's nice. Places in Poland as well, and we have, and Skinnakas is not there yet. I have to update the map because we've just added it, right? So is your telescope on the map, right? If it's not, then get back to us. We would like to add it. So that's the whole point here. Just to show you some examples, these are some pictures of the telescopes we work with, different sizes, different setups. And this is the light curve of one of the objects we observed. This is actually not a Gaia target. This comes from Assassin. So it's a very funny microlensing event. You see a crazy light curve. On a timescale of a couple of days, there were very dramatic changes over multiple magnitudes. It was actually reached 9 magnitudes. And then what we have in the light curve, each point has a label. This is the time, this is the magnitude, this is the person who observed it, and then you can study this particular data point. And we have, for that particular event, we have 3,000 events. Yeah, I'm wrapping up slowly. Okay. And as I said, we cover multiple science cases, right? That's the point. We are not focusing on supernovae only. We're not focusing on TDEs only, or even microlensing, which we like in particular. But then you see, crazy CVs, right? This is the current data. This is the follow-up data. This is the archival data. This is an example of a flare here at the bottom in a quasar, right? And then you also, for free, you can very quickly have a look at the NEO-WISE data here at the top of this figure. You see that there is some coinciding behavior on long-term evolution of the photometry. We have AGNs and quite a number of microlensing events which do very crazy things. A couple of examples of the image processing. So this is the core of our pipeline, and this facilitates the data to be not spending hours or days on the hard drive somewhere, but it's just shipped to us as soon as possible. That can be fully automated. So uploading your data from your telescope, there is an easy script you can set up, and all the data goes to us. And then we take care of the processing. We measure all the stars on the image. We do the PSF photometry or aperture photometry, whichever is most suitable, and then we standardize it. We find automatically we find the best matching filter. So even if you observe in a very weird filter, we can sort it out. So you see here some examples from smallish telescopes like LCO, GO Chile, and then LCO 1 meter. And then there is also a supernova observed by SOAP, which is actually our observatory next to school. So that's a very nice example. And then the data is, of course, downloadable. Everyone who's registered, and we keep track who downloads what. But it's registered, so there is no paywall yet. Well, we've been thinking about PhDom Pro, maybe some other time. In terms of thinking about funding, right? That would be premium, yeah. So some more examples of some beautiful data we've collected. So here you see very smooth light curves, and each data point was collected by a different observatory. Okay, so some statistics, and I've just done a summary of last year. So we processed 85,000 images. And actually, I was quite surprised, partially only, that 25% of our data was collected by one observatory. There is a person who will speak. He will have a remote talk. Josh Hamsch. He runs his own small observatory. It's located in Chile, and he commits a lot of data to us. So 25% of data comes from that small observatory. The other 25, however, comes from LCO network, where we have ongoing collaboration and proposals as well. However, what I want to emphasize here is that half of our data comes from a huge number of heterogeneous telescopes, right? If we only limited ourselves to LCO and Rode, we would only get half of what we are getting, right? And then the rest are actually people contributing smallish numbers of observations. They build up this vast amount of data we have, right? So that's what I wanted to emphasize here. So at the moment, we process something like 5,000 images per week. I think we can handle more at the moment. Can we? Yeah. So again, the question is your telescope on this chart and is observing with us? So as I mentioned, we are robot ready. So we have programmable access to all features, all functionalities of PhDom are accessible via API. And there are scripts provided. You can just download them and run. For data flow to from telescopes, observing requests, image uploads for processing, and so on. And we are very happy to help and guide you. And I will advertise here a short session tomorrow morning for, well, whoever is interested. We'll have a kind of hands-on session, how to do things, how to create your targets, how to add them to the system, how to upload your data, how to download it, and how to script it. So there will be a dedicated 2 hours tomorrow morning if you're interested. AstroColibri is a perfect example of that system. So you have an account on AstroColibri, and then you create an account on our system, and that's the only way you need to communicate with PhDom, because then you can just click a button on AstroColibri, and then the target is created in our system, and all the data is then being transferred to AstroColibri. You'll hear about that system from Fabian later. And as I said, we provide the ready scripts, and there is a documentation for all of this. One more slide about thinking about gravitational waves. So we haven't done this yet, but in principle we are kind of ready for this. We can respond to multiple candidates for gravitational wave counterparts on both hemispheres. And then we have also archives. I think that's the advantage, because we can very quickly, in an automated way, we can help you rule out some of the candidates. And then we also do automated data processing. So if you have a candidate, you just observe a patch of the sky and we can quickly process it, and then you can have a confirmation of a rejection. And also, we are not afraid of the galactic plane, nor is Gaia, but we can also observe the galactic plane and find counterparts there. I think which was a problematic bit for surveys so far. BHTOM newsletter. Some of you are already using this. This is something I send every Monday morning. So there is one already being sent this morning, which gives kind of an overview what's going on in the system. So it shows what are the targets, new targets we've added in the system, what are the targets, just roughly speaking, for the southern hemisphere and northern hemisphere, which are currently now of interest. Many people find getting an email, a bit more personal, and in a more friendly way. We also give the statistics, what people submitted. You see Josh Hamsh winning that for that week. I don't know who won this week, the previous week. We'll check. We'll check later. Also, we can, if you want, we can design a dedicated email stream sent to your mailbox also Monday morning, where we just we shorten the list of targets visible from your site up to your magnitude limit, your air mass limit, and so on. We can talk about it. It's a dedicated email to your observatory. Some people actually ingest these emails automatically in their schedulers, and then they can schedule observations for our targets. Speaking about future, so we had a very productive week last week, sitting down with BHTOM people, Las Cumbres people, and people from Forth, and we've designed a new concept, and we actually have to call it BHTOM 3. There's no other way. So the thing is that we're thinking about scaling up. The system is now functioning quite well. However, we have to scale up. And the idea to scale up is that we are thinking about a more distributed system. So the core of the system remains the same, like it's drawn here. The BHTOM 3 TOM system remains as a TOM, maybe slightly lifted, with a lifted design. It is also capable of processing your data, right? So you see all these telescopes at the bottom. So these are the telescopes who send data directly to us. We process it, we calibrate it, we store it. But that bit will be a little bit independent from the whole core system. And then there is a central repository of all the observations we process. So we use it directly in BHTOM, but also it is then stored in a central place where other nodes of processors are also contributing. So in a way, it is similar to what we have now, is that the central database is currently within our system. We want to separate it so that then some of the processing of the images can be done on your side. And as we always, our guinea pig, they're trying to implement it on their side. As I said, they're one of our major contributors. So if the processing can be taken care on their side, and we only get the end product in our database, this will actually allow us to increase the number of observations we process. And then the same applies to any of the telescope partners we have. If you are interested and you have resources, we can install the Dockerized version of our pipeline, just essentially click install, and it's there. It's set up very quickly on your local computer, where you process your own data and you just submit your data to our system. So that's the idea. We also hope to move to multi-messenger targets. It is actually related with the ACME funding Jerry mentioned. So we will be following the alerts from multi-messenger systems, not only gravitational waves, but also neutrinos and others. We hope to include the solar system objects, which we don't yet. Then we will expand the list of archives we query, also going to multi-messenger regions. And if you have any more ideas what should be included, that's why we are actually here. We would like to hear your feedback. What's your experience on current use of BHDOM, on current version of it, or what do you think what would be useful to have? There's always many ideas we bring from these meetings. That's why we would like to hear from you. And also grant funding ideas, if you have any, right? BHDOM Premium is one of them, but we don't want to go that way. We would like to keep it as simple as possible and as accessible as possible, free of charge to everyone. I think this is the only way science can be done these days. My last slide, I think, is the announcement. We already know where we go next year. So it's not going to be Crete. We will come back here, I'm sure. But we have already secured a place for next workshop, and it will be within the ACME framework. So we hope to remain the numbering system, so it's going to be 16th meeting. However, there will be a bit more focus on time domain astronomy, alerts, and archives in the form of a hackathon in a way, and it will be held in IAC in Tenerife, roughly September next year. And I'll stop here. Thank you.
Thank you, Łukasz. Any questions, Staszek?
Actually, I have two. By raw images, you meant the calibrated images, right?
Raw images, in our sense, is we know you do the flat fielding the best way you can do it. We will not dare doing it.
And the second one, you mentioned that any feature transform to Gaia photography. Some time ago, I provided square wave photography, and it was pretty fun, so I stopped doing that. Has it changed?
We've added some features that help deal with this problem. I can show you how do we deal with this. Yeah.
David?
In your schematic showing how black hole Tom sends instructions to other telescopes, etc. I was just wondering, does black hole Tom therefore have like AON, part of it is AON, or is that like a separate thing?
Well,
maybe it's a question to
yeah. I'll try to answer and then let Rachel comment. So the question is whether BHDOM contains the EON. By default, it does, because it's, that's why we use Tom toolkit of LCO, because everything comes in for free. It's essentially embedded. It's EON ready. So if your telescope is talking about, is EON compatible, and you will hear about EON if you don't know what it is. It's essentially a protocol to talk with the telescopes. If your telescope is EON ready, we are ready to talk with this telescope. And we hope that BHDOM 3 will be even more compatible with that than it is now.
Okay, so it's more like it's a protocol rather than an actual lump of software that's separate to the Tom.
Yeah, it is kind of another. Highly compatible.
That's it.
Okay, you mentioned, I didn't quite understand that people who like number software and installing. Is this sort of like the whole candidates pipeline? Or
Yeah. So the idea is that we will soon make it possible that people can download the processing and calibrating unit as one installment, right? And that will talk to us. But all the processing will be taken care on your side. And we would be really happy to have this installed here on Skinakas. Because other way around is that you can always submit your data through our processing pipeline, which will remain. So if you don't have any resources to process your data, then you can always send it to us. But if you are interested, then we can have it installed, and we would definitely be interested to have it installed here. So have you as a node for processing. It's still work in progress, but it's going to take place soon.
Yeah, in some of the light curves you showed, there was not only optical data, but also infrared. So does it mean that when an object is entered into black hole Tom, you automatically search what is available in your database?
Yes, exactly. That's the idea. We search through optical archives. We search through NEO-WISE infrared data, TUMAS infrared data. We go to radio archives as well. We hope to expand to X-rays, and everything what's publicly available. It's a huge resource. I think it's underused, but it's done automatically.
Thank you. I think if there are any more questions, you can ask them to Łukasz over the coffee break that is starting right now. So we'll meet each other here at 11. And for those of you who are having a talk in the next session and haven't uploaded the slides yet, please send it to Łukasz. Thank you very much.
I have my talk for this afternoon.
Yes, in a second.
And to whom should I talk for the black hole talk to load up some images? I suppose somebody must be here.
Yeah, well, you talk to me or you can talk to Przemek. Here, Przemek? You can talk to Michelle then first about data.
Is there any chance that can you check if you can download my slides?
I need to switch this on because we are
Uh, just testing if it works, if the sound works.
Nada,
Yes,
say something.
yes, Nada, we could hear you, but
Say something, Nada.
hardly.
Wyłączone jest.
Ja w razie czego mam jakieś
But I heard her.
Ale
But
to,
it's
ale to
very
jest
weak.
dla całej sali, to...
Bo ja nie mam żadnego
It's not enough.
Hello. Testing if speakers work. Does it work? Can you hear me? We are testing the sound. Testing.
Hello, am I audible? Hello. Hello.
Hello. Sorry, Rupa, can you say something again? It could also be on our side. So we just need to check something here. Just a moment. Yeah, so since online you can hear, so that means we have a problem. We'll be right back.
Hello. Am I audible now? Hello. Hello, can you hear me now? Hello.
So I think, so the problem is on our side, since Fraser, you could hear Rupak, but we're
No,
getting better speakers, trying to see what we can, how we can work.
I think there is a problem from my side as well. So,
So-
I will be showing my slide from one computer and I will be talking from another one.
No.
So is that possible?
So Rupak, it's not really a problem on your side. The main problem is here because we don't have a good audio system. So it's impossible to. It's really hard to hear you, but it's because I'm standing next to the speakers. But we will try to sort this out soon.
Oh, let me know. So should I close now?
So let's wait a minute. Let's wait some like 3 minutes, okay? So because we are setting up the system, so then we will test
You might
it.
want to change the order. We have local people to speak first. That will give us some time that they bring the
Ale pan
speakers.
przynosi też.
Cable.
Czekaj, ja się odsunę.
Aga, pilnuj tego, bo ja nie będę tego pilnował.
Wiem.
Żeby ci to tu załadowali, bo ja nie jestem od tego.
Ale dali ci... Zgrałaś?
Tak.
I jak się nazywa?
Aga,
W katalogu Aga jest po prostu mój...
Aga folder.
Jest Aga folder. Mogę iść, Siusiu?
Możesz iść, aczkolwiek ja też nie jestem od tego, nie wiem kto jest od tego.
Dobra, ja to
Ale dobra, my to zrobimy.
Niech leży.
Niech najpierw, bo najpierw musimy rozwiązać sprawę dźwięku.
Dobrze, dobrze.
So it's okay now, right? It should be fine. Okay. Kabel zmieniony.
O, i działa jeszcze.
Ale słychać coś?
Nie no, na razie HDMI, to jest pierwszy problem.
Ale jeszcze ktoś przyjdzie od głośników, czy nie?
No, powiedziałem o głośnikach.
Confirm your speaking language. A tu jest prezentacja Agnieszki.
A może Agnieszki prezentacja
Która będzie
zgrajmy?
teraz. Graj sobie, nie wiem gdzie tam zbierzesz. W folderze Aga.
I think it's better without the speakers. From the laptop it should be louder.
Maybe.
But HDMI will connect to this.
Yeah, maybe without
What do you mean?
This. So you're connecting this now to the projector with HDMI. So maybe the projector.
No, because now we have here USB-C and it's not for the sound, I think. The sound is only with this.
Yeah, no, you're not right.
No?
Yes, I know what you mean, and we can actually make
You
a
have
speaker
HDMI
Epson.
here.
You have.
Wait, no, that's okay. You see, that's
Yes.
Epson.
Yes, exactly. So this
Yeah,
is
we
what
can
I
have
thought.
output through that.
Yes, it should be better.
And microphone as well.
And with their speakers.
Yes, we
Well,
are.
let's try.
Za bardzo.
Raz, dwa.
Granie?
Śpiewa.
Nie, ale to stąd zbieram.
Nie, ale to poczekajcie, bo ktoś musi stamtąd kupić, nie?
Zrobiłeś wolną maskę? No, test można zrobić. Nie leci dźwięk z tego. Nie leci dźwięk z tego. Koleś powiedział, że leci, ale nie leci.
Ale
Tu stoi.
ale jest ten, ale jest na...
Popatrz, gram tutaj test na Epsonie, nie? Jest jeszcze drugi Epson. Spróbujmy ten.
Fraser jest, albo Rupak?
Yes.
To coś powiem.
Okay. Fraser, are you there? Can you say something, Fraser? Or Rupak?
Okay, can you hear me now?
Yes, we can.
Okay, I will test once again, please.
And Rupak, I think Rupak is also.
Can you hear me now?
Yeah,
Yeah, I
that's
can.
good. That's very loud. and
Okay. Yeah, okay, okay. So I will use this one.
Yeah. Yeah.
Zgraj prezentację.
Okay. Fraser, can we test your sound and screen?
Tak, jakiś kabel przyniósł i się okazuje, że tam
Hi, Wukash, can you hear me okay?
Yes, we do hear you, Fraser.
Fantastic. And presumably, hopefully you can see my slides as well.
We
Although
do, we do. Yes, all
not
seems
in.
fine. We start in a minute.
Yeah, no worries at all.
Nie, już. Ale nie minęło spuściło. No nie wiem, są przysłowie
Hello, everyone. We have a first talk that's going to be delivered remotely. The talk will be by Fraser Lewis from Fox Telescopes, and he will be talking about using Gaia alerts to persuade schools to use robotic telescopes. Fraser, can you hear us well?
I hear you absolutely fine. I hope you can hear me as well.
Yeah, we can hear you and we can see the presentation. So, yeah, let's start.
Okay, no problem at all. Thank you very much. Lovely to be invited as always. Shame that this time it's not in person, of course, and apologies for those of you watching in the room. I know watching online videos of people in other parts of the world is not always perfect, but yeah, please do shout if there are any things that I say today that you want to ask about or follow up. Do drop me an email. My email will be on the final slide, so please do that. Yeah, today I'm sort of talking about Fox Telescope Project as well as our spin-off company, which is kind of important. Doesn't sound like it would be, but it is, which is called FTP Europlanet. It's a German-based company that does effectively what Fox Telescope Project does, which is providing telescope time and providing telescope resources to students and teachers. The reason it's important is because, as I'm sure you know, Germany is in the EU, and also, as you probably know, the UK isn't in the EU. So that was something we set up just to have a way of continuing to work with our European colleagues, if that makes sense. I'm also tied in with the Schools Observatory, formerly known as the National Schools Observatory, which is based up in Liverpool, tied in with the Liverpool Telescope and their resources and educational program there. And I'm also a tutor for the Open University, and I know you'll be hearing more about the Open University in Ben's talk, which I think is coming up next. My final affiliation for today, apologies for all the affiliations, is GWAM Astronomy Modeling, GWAM. I'll come back to that one as we get through the slides. You'll be hearing from Rachel today as well. So Rachel, I'm sure, will do a far better job of detailing the LCO network and its capabilities and its plans for the future. But just really to remind you that as Fox Telescope Project, we have access to our two meter Fox telescopes, the red dots there in Haleakala, Maui, and in Siding Spring in Australia. The yellow dot, of course, represents the Liverpool telescope in La Palma. Again, Rachel will cover this in more detail, but the LCO network is far more than those 2 meter telescopes, as I'm sure you know, with the 1 meter and 40 centimeter capabilities as well. I thought I'd just go through a handful of highlights. I'm probably not even going to cover the full 15 minutes, but I thought I would mention these just as kind of things, Gaia-related things that I've done in the last year or so. So these are 4 different astronomy online and face-to-face courses and conferences that I've been involved in the last year, with the numbers of teachers involved. So 3 of these are face-to-face, the top 2 in the list, as it were, the Astronomy Adventure in the Canary Islands, and the work that we did with our colleagues in ESA and Madrid. And in each of those, I've mentioned and sort of heavily pushed Gaia resources, talked about Type 1 supernova, Type 1a supernova, and so on. The last one, GEHU Global Hands-on Universe, was an online-only conference that ran last week, again, to educators throughout the world. I'll mention this one. Last Skill was a project that we worked on, which finished last June, working with colleagues in Greece, in Portugal, and in Austria, and developing online and digital resources. So again, this was Erasmus Plus funded. Our idea was to support teachers, you see it on the screen there, hunting around for data archives and big data and so on, things that Gaia obviously ticks some very, very obvious boxes on. We produced what we call demonstrators, which are sort of lesson plans, and then we encouraged our teachers to create their own lesson plans on top of that. The one that I'd say it today anyway, of course, wouldn't I? But the one I'm most proud of is this one that I created called Using Gaia Alerts. It's a PDF or it's an online resource. If you follow that link, you'll find it. And it's just talking through the different parts of kind of the scientific method, you know, how you would find a target, how you would take images of that target, how you would process the data and the conclusions you reach. So the scientific method, but sort of pushed down, squashed down into something that schools and students can work on. So that's what I created last year. Again, I'd encourage you to have a look if that sort of thing is of interest to you. The one I thought I'd mention, because this is, you know, we all know sort of Gaia's status, but of course we are talking this week about, you know, what comes from Gaia and what's next for all of us. And this is a group of people that I worked with, kind of started up during the pandemic, where of course we had no option but to go online. And we work with a group of educators and students from around the world. We have people in the USA, myself in Wales. We have students and teachers in Chile, in Pakistan, and Colombia. So we're worldwide. We're not huge. We only have probably 6 or 8 students at a time, but we are working very intensely with them on a range of different projects. But we realize there are sort of 4 or 5 of us that are, I want to say the word expert. I don't want to say it too sort of loudly, because our students know as much as we do on some of these areas. But there are 4 or 5 of us that I guess kind of try and guide the students in various directions, which is a bit like herding cats, as you might imagine. They are very independently minded, and we run with, you know, their ideas as much as we run with our own ideas. But aside from that, we are creating a series of resources, and you see it there in the little sort of slide, or the little JPEG on the right-hand side of the screen, albeit that's in Spanish, which is basically setting up the basics. What are the basics that students ought to know to do astronomy? So understanding things like Stellarium, which is an online or planetarium software, Salsa-J, which we use for photometry, and then taking them a little bit further into image processing, and then starting to push them a bit into science. So again, currently in English and Spanish, but there are no reasons why we can't start thinking about that into other languages. The key here being that you know, there's only a few of us doing this. There are only a few of our students that we speak to regularly. However, if we start to put resources online, that scales an awful lot more easily than our time, if you like. One of our students has been working with TopCat, which I'm sure many of you know, sort of a super version of Excel, if you like, and has been using TopCat in conjunction with LCO images and the Gaia DR3 catalog to produce CMDs of open clusters, and to compare what you see from an LCO image, or, you know, a standard telescope image, if you like, with what Gaia DR3 returns in terms of data and data quality. So she's been doing that for a little while now. We are currently supervising her writing a paper, which we hope to submit soon to the Astronomy Education Journal. And it's much more about the paper is much more about the process of creating of the scientific method than it is about the results. So we're not particularly hate to say it, but we're not particularly interested in the shape of the color magnitude diagram or the main sequence. We're much more interested in the process behind getting to that point. So we hope our referees will understand that and see that favorably. In recent news, I've been looking at one of the potential microlens sources, 24FS, and one of our teachers has been doing that as well. We are using a different set of LCO time. So LCO, as you probably know, provides time on its 40 centimeter network to various educational groups, and GWIS has a set of time on there. So we're using the 40 centimeter telescopes, which means that we kind of enjoy those really bright objects. You know, the 2-meter telescopes, we can go quite deep, but on the 40 centimeter network, obviously we're a little bit more limited. Please keep sending the weekly emails. I see today's one has arrived, so I will have a look at that today or later, I promise, Łukasz. We also look for targets with Astro Calibri, which Fabian mentioned to me last year, and I think he's talking again tomorrow, so do follow Astro Calibri. It goes on a phone, and if there's one thing you know about students, it's that they love being on their phones. So if we can get them on their phone doing something that's sciencey, you know, that's a positive. Again, with our German group, we've recently started another Erasmus Plus project called Astro Journeys. This one's involving the IAC in the Canary Islands, Sergi in Paris, who are leading it, our colleagues in Nucleo and EA in Portugal and Greece that we've worked on many projects with, as well as the OAE, which is in Heidelberg in Germany, and us as a German group as well. We are developing the big ideas of astronomy. So we'll be looking at the big ideas of astronomy. We'll be looking at online resources that exist and trying to pull them all together into one compository, if you like. So one place that you would go to find your big ideas. And as a part of that, we'll be running a couple of summer schools next summer and the summer after, both in the delightful places of Marathon in Greece and in the IAC in the Canary Islands. I'm sure you can hear the helicopter overhead. I'm hoping they're not after me again. Łukasz did ask about BHTOM feedback. I don't really have any negatives. I've been in contact recently with Łukasz and Zemek on different things within BHTOM. We are delighted that our data drops onto plots without having to do the horrible photometry. However, you know, we all had to learn photometry, so we make sure our students do as well, because again, you know, you do need to know what's going on behind the black box. So we are working with our students to get their heads around things like AstroImageJ and so on. The fact that those data points can drop in with individual user names on is really nice. As you know, from conceiving of writing a paper and getting some data to actually writing the paper and having it published, you know, I want to say 2 years. Some people do it in less, some people do it in longer, but you know, it's very instant science that data can be taken by our telescopes, grabbed by BHTOM and, you know, dropped onto the graph. And the point I didn't mention there that I probably should have is the collaborative nature. You know, those 5 data points of mine are of no use to anyone, but when combined with the data points from other users on BHTOM, then we start to build up the big picture, and that's a really important lesson that we think our students should know. You're going in the right direction, obviously, because, you know, our students love black holes. They love the sort of type 1A supernovae, you know, the linking with cosmology as well. We are currently looking at objects such as blazars. We're currently looking at LMXBs, which is my research area, and micro-lensing events as well. So we've got students dotted around that are playing around with all these different things and trying to understand the background science of each of them. That's it, really. For all the help and support that you've had over the years, I wanted to say thank you in as many languages as I could find. I don't think Welsh was on there, which is why I put diolch at the top, which is Welsh for thank you. Efaristo is in there as well. So yeah, thank you to Łukasz, to Jerry, Simon, Zemek as well, and all the people that are working on Gaia Alerts and BHTOM. And I'll leave you with my contact details if anyone wants to get in touch. Thank you very much.
Thank you, Fraser. Do we have any questions? I wanted to ask about the big ideas of astronomy. Is that the same that was related to International Astronomical Union Office for Education, or is it a different project? Because there was the same name of the project that was related to some, like, picking up few ideas in astronomy and giving some special explanation, and publishing is as something that should be used as a basic for every citizen's literacy about astronomy or something like this.
Yeah, I think we will use that as our basis, but this is a different project. As you probably know, with the Erasmus Plus, you can kind of, I don't want to say reinvent the wheel, but these things kind of come around in cycles. So we'll be doing our own big ideas of astronomy, but we will use that IAU guide and various other guides that are out there. The issue we have, as I'm sure you know, every single country has a different curriculum. So pulling together the big ideas, we'll do that for our partner countries initially, but just as by way of example, in the UK we have 4 different national curriculums, so it's pulling together all that information. I know in Germany as well they have different curriculums in all the different provinces. So yeah, we'll use the IAU as a starting point for sure, but I think we'll go further with it than just that.
Okay, thank you very much. I didn't see any hands up, so we still have your contact details at the screen. So thank you very much, Fraser.
Thank you.
And we are moving to the next talk. That is also an.
I don't see Ben.
Okay, so I think we.
Maybe
yeah. So we skip the next talk because we cannot see the speaker online. So the next talk will be delivered by Agnieszka Słowikowska. Is obviously here. It's going to be about the Jive and ORP. And we should zmienić, jak jest speaker tutaj, to trzeba zmienić.
Szerowanie już wyłączyłem, włączyłem. Szerujemy tam, mikrofon włączony, kamera tu.
A mogę mieć ten prezenter już?
Tak. Tak, oczywiście.
Okej.
Jeszcze tylko
A u mnie się, no to jest zawsze, tylko tu i
A z tym filmem to najwyżej mi pomoże, że coś tam nie pójdzie, nie? I will try not to. Yeah, I don't know. If they go to. Oh, no, I will be quick. I will be quick. Yeah. Welcome everyone. I'm Agnieszka Słowikowska, but you're welcome to call me Aga. It's absolutely fantastic to be here because I spent quite a few years here in Skinakers, also as a postdoc at Ford. So it's really, really great to be here. I'm from Jive now, and I wanted to give you some introduction to the EVN and Jive, and also what we have done in ORP, so in the OPTICON-RadioNET pilot project. Does this work? No, I don't know. Maybe it's work. Yeah. So to start with, maybe it's good to understand what the Jive acronym stands for. This is the Joint Institute for Very Long Baseline Interferometry, ERIC, which is the European Research Infrastructure Consortium. And I believe the most famous now result coming from the VLBI technique, observing technique, is basically the shadow of the black holes from M87 and also in our galaxy Sagittarius A star. And I just saw in the newspaper that they already have this 3-frequency image of the black holes, really cool. And former director of Jive, Professor Hauptlange-Velde, he's now the EHT project director. So this Event Horizon Telescope Consortium was delivered those images of the black holes. And of course, it's because this provides the sharpest view of the universe with the resolution of tens of microseconds. So just to position ourselves, like where EVN stands, when you have the long, of course, the radio domain covers really wide ranges of the frequencies or wavelengths. So if you want to observe in the long wavelength, you basically use LOFAR, and now they present really wonderful results from the black hole jets that really, they are huge megastructures, like 140 Milky Way galaxies when you put them one after the other, and they are like 10,000 megastructures discovered by LOFAR. So then you basically, when you want to work on the megaparsec scale, you go to the long wavelengths. Then something in between, you know, well, something on the level of centimeters. This is the regime where basically Effelsberg telescope, 100-meter fully steerable telescope in Germany operates. Then you have the British network Merlin and also EVN, which stands for the European VLBI network, and we operate basically in the centimeter wavelengths. And then if you go even farther, so that this is the results which were obtained by the EHT collaboration, so Event Horizon Telescope, with the millimeter wavelengths, now even with 0.87 millimeters, which is 345 gigahertz, and also the GMVA, which is the global millimeter VLBA array. So these are the telescopes. Yeah. These are the telescopes that constitute the EVN network. So there are more than 20, and they are spread in Europe, Asia, also in South Africa, and until 2020, also the 300-meter Arecibo telescope was also part of the EVN network. So how JIVE relates to that? So we are an ERIC, and we are the central organization for the EVN. There are more than 20 telescopes from many countries. ERIC itself has 7 full members and 3 associated partners, and we are hosted in the Netherlands, and we are located in Astron. So these are the countries: Netherlands, UK, Italy, Spain, France, Latvia, and Sweden. They are full members, and associated members are from China, Germany, and South Africa. So we have, you know, our main point is basically to support VLBI in very broad context. Also, like, you know, to support the EVN users, the radio telescopes, implementing the new equipment and procedures, advocating for the new partnerships and collaboration, and also community building and support. And of course, we also we provide the service to the EVN Public Data Archive, R&D, and for the JIVE EVN partners, and also to engage and represent EVN and JIVE in the EC. JIVE was founded in 1983, and in 2014 we became an ERIC. For a long time we have been the only ERIC, astronomical ERIC, until September last year, when LOFAR became a LOFAR ERIC, and the next ERIC to be is the Cherenkov Telescope Array Observatory. There are now 20. So we are just finishing the second cycle of an ERIC, because this goes like in 5-year cycles, and next year we will start the 5th cycle. Why is it? What are the advantages of being an ERIC? So you can think about of a few things. First, the commitment is on the governmental level, so it's you know, takes a lot from the liability, personal liability. Also, we are quite flexible in structure, so you can be a full member or associated members. You can have the full memorandum of understanding or as an associated partner. If you are a full member, you have to agree for the European Law of Justice. And then you also have the VAT exemption, which is very handy if you are going to build the hardware. For example, in case of LOFAR, they are now, LOFAR does not observe for the moment, because they are upgrading from LOFAR 1.0 to LOFAR 2.0. And Cherenkov Telescope Array also wants to use this VAT exemption, because, you know, this makes either cheaper or you have more money to spend, right? Whatever you decide. And of course, we have the recognized status in the EC, and we are eligible for the EC funding. And we also coordinate the distributed research infrastructure. LOFAR ERIC is distributed ERIC with the hardware. JIVE ERIC is the single-site ERIC, and we don't really own any radio telescopes. Okay, the only thing that we own is the correlator that correlates the data coming from the radio telescopes. So this is how ERICs are organized. Now they are 28 already, and they are organized in clusters where you have the energy, environment, physical science and engineering, health and food, and social and cultural innovation. And here you can see the map basically of ERIC. So the black symbols, they indicate where the ERICs, which country is, and the institute which hosts the given ERIC. And with different colors, the different clusters are indicated. So you can see that the second color shows also the jive and LOFAR ERIC. It's quite complicated structure because we have the EVN, so the directors of the radio telescope, they sign a memorandum of understanding, and they dedicate 70 days of observing time over a year. But this is not the legal entity, so legal entity is JIVE for the EVN, and unfortunately not all the partners of the EVN, they are also JIVE partners. So you can see there is the list of the JIVE partners and also the EVN partners. There are also countries that are aspiring to get to the EVN network. And in JIVE itself, we are organized in a way that there is JIVE Council, then there is director, and there are the departments. So one of the countries which I hope will join this year still is Thailand, with their wonderful, just commissioned 40-meter telescope in Narit, and they also have the L and K receivers, so they will. We hope we will get the first fringes basically still this year, calendar year, and that we will progress with this. So the EVN, this is a global network. It still has the highest sensitivity, and also it provides the very unique observing mode, which is real-time observation. So we are then correlating the data in real time. We operate in the frequency range from 1 to, let's say, 40 gigahertz. And the key science are the black holes, fast radio bursts, active AGNs. Wait, this does not work, sorry. A star-forming region, TDIs, and also gravitational lenses to these planetary bodies. I mean, there is a lot of science that can be done with the EVN. We also allowed this real-time observations. And last but not least, it's open sky. And this is something which I believe it's a policy that was always there since early beginnings, since the 80s, last century. And here is the proof that people, they are really using EVN, because you can see that this is the geographical distribution of the EVN PIs. From 2014 to 2024, you can see that the PIs are at least from the 30 countries, whereas also co-PIs could be even from more countries. So if, something for the observers. We have 3 deadlines for the call for the proposal. It's 1st of February, January, and October. You go to the EVN webpage, /EVN for astronomers, and then you can find all the details. So the first steps, the technical capabilities, and also latest updates from EVN and EVN data archive, source finder, latest call for the proposal. So all the documentation is there. And also you can join our e-training, and we come back to that at some point. So this is the kind of summary in which frequency ranges we operate as EVN. We also have, as I mentioned, this real-time observation, so basically correlation in real time. We are normally organized in 3 sessions, so it's roughly, let's say, 3 times 3 weeks, plus 10 times 2 days, where we have this EVN, so then the data are correlated in real time. You can have targeted observation or TO, so TO or short observations. You can ask also for this out-of-session observations, so this means basically EVN observations. And you can have different correlation modes, from continuum spectral lines, pulsar observation, and multiple phase centers. So this is how we are sorry, no, it's not this slide. So we have, EVN provides more than 1,000 network hours per year, which is more than 1,200 hours of correlation hours, and we have almost 200 terabytes of the EVN data archive. There are more than 3,000 publications that at least mention EVN network in the paper, or they are based on this data, or they refer to the results. And there is more than 500 publications where JIVE is affiliated. And there is 110 experiments, and we have already had 44 support scientists, which is really great because they come as a postdocs. Half of their time they work for their science, but half of the time they give the support. And then, if they move, and I would say that we have pretty high success rate, that more than 90% of them, they find the next job, the next postdoc, and they continue. So this is how we are organized. We have 5 departments. The head of the department, Maroline, of technical department and R&D is here, and she will give the talk after me. We provide a lot of support from, starting from the EVN science support, but also for the user support, which means basically whenever you need to put the proposal, you can come to us, and we will really support you from the idea that you have. We will check if this is doable, and then we will help you and advise you how to write the proposal, and then how to schedule the observation. The observations will be performed. We will correlate the data, and we will also help you in the interpretation of the scientific results. Of course, we have this R&D department that works on the new modes, wide field of view, and real-time observations. We provide service to the JIVE partners and also to the new EVN members. And we also, of course, engage and represent with the EC. Last but not least, we put a lot of effort on training, and you can see exactly, today it started the 10th ERIS school, which is the European Radio Interferometry School, and we are one of the main co-organizers of the school. And last year we have been organizing CASA school, and they will be in like 2-year slopes. So either there is CASA school or there is ERIS school. So next year there will be a CASA school, and if you want, you can join. We put a lot, as I said, we also host and co-organize EVN seminars. This is something that come up during COVID time. So you can go to the YouTube. You can either join the EVN seminars on Zoom, or you can go to the YouTube and then you can watch them later. This is the distribution of people that have attended this EVN seminars, and the next one is coming in October 24. Last, but this is pretty important. We also now provide the e-training, so you can join in training how to start using EVN. And for me, what is really interesting is that you can see already how the participants are now at least from 33 countries in the last EVN training. But you can also see that there is huge interest from African countries to learn, which is kind of something to be understandable when you are building the biggest radio infrastructure in Africa. I think that this is basically the output of the SKA. So, and the plan is that from next year we will have at least one e-training per year, just before some of the call for proposal. Here are the numbers, but we can skip it. And of course the science. So there is a lot of science that can be done with EVN, and starting from the AGN, stellar masers, transient, especially FRBs, and then space instrumentation methods and data analysis. And we are also involved in the EHT, but as I already mentioned, here are some key science examples. So there is also EVN is used for geodesy and for the tidal disruption event. There are also, of course, it's a great instrument for the astrometry if you want to determine the orbits. So one of the examples here, the astrometer of the brown dwarf. And there were also observation of the gravitational lens and also the location of the FRB. These are very recent papers from JIVE, where also divers were involved with the accretion of the black holes, but also detection of the precession of the jet in M87, and also determination of the strength and structure of the magnetic field in the black holes. Also Keplerian disk, these are the major studies of the Keplerian disk around the protostar. And of course, we are really strongly involved in FRB studies. I think I can skip it because maybe Maroline, she will introduce herself. But yeah, basically, we give the support for the software correlator, EVN storage, network connection, virtual machine archive monitoring system also during the EVN observations, backups, and then R&D development in the science capabilities, calibration tools, and data transport, and data processing. These are the, Marwine group, she managed to put the EVN archives also in the virtual observatory, so you can use VO to check if there have ever been observations into that. And then we also are we are involved with the Astroflash, so the FRB, EHT, I already mentioned this. With CRAF, I will come back to that, and we are also involved in the ESA JUICE mission for the near field VLBI. And basically, what it does, it will help us to get the proper parameters, orbital parameters of the JUICE with the very high accuracy, and this will let us to study the gravitational fields of the icy moons. For CRAF, which is the Committee on the Radio Astronomy Frequency, we are also within ORP strongly involved in the group for protecting the dark and the quiet sky. And why do we do it? I wanted to show you, this is very fresh, recent publication from LOFAR, like last week, I believe. And this is what LOFAR see from the Starlink second generation. I hope this movie will. Will this work? Okay, so you see these bright spots, right? And all of those spots that are fast-moving spots with the red cross, these are the Starlinks. And they are 34 times brighter than Starlink's first generation. Okay, how do I do it now? But I don't see anything. Okay, so you can see, I mean, those which are marked with the red cross, they are Starlinks because the orbits of the Starlinks are public. You can go and check. And the point is that now, if you compare it to the optical domain, it's like, having the faintest source that LOFAR can see is like, let's say, 6 magnitude star, and the Starlinks with this brightness is like a full moon. So this is right, and now we have just a few thousand of Starlinks, but there are going to be 100,000 of Starlinks. So for us, of course, and it's very serious. And the point is, most likely, I mean, there is an interesting fact that they are seen only in the daytime. So we think that this is because of solar panels. Basically, the solar panels, they just act like an antenna. So as Jive, we also host the frequency manager. It's Valit Matkur, who's working with Craft and basically is taking care that we will have a bit of the radio spectrum still to observe. Okay, we are also, so for a long time, I mean, it's like radio astronomy have been collaborating together a lot already since 80s last century, and we started with IRAM with the millimeter wavelength collaboration, then with EVN. We got already support from the EC grants in FP2 and FP5, and then in 2000, more or less at the same time when Opticon was formed, we formed the RadioNet, and for 20 years we have been providing transnational access through the EC funding as a RadioNet project. And then, in 2021, we changed the RadioNet. It's not the project anymore, it's now RadioNet Consortium under the formal agreement. So basically now we are collaborating at more than 20 institutes, radio institutes together, hosted in Europe, but not also. And of course, I mean, we also have partners like SKO. Maybe quickly, just how do we address some of the problems? So the transnational access has been provided to the users through the former RadioNet project, but now with Opticon and RadioNet, we have this ORP, and now Łukasz also mentioned ACMA, it just started the 1st of September. Then the next generation technologies of radio astronomy infrastructure, we employ this by the Infratech Core, so there is radio block. There is also a strategy plan for the European astronomy, and we are in the Astronet science vision and infrastructure roadmap. We also have, we are on the S3 landscape, and we have two ERICs, Jive and LOFAR ERIC, and also SKO. And now we are also starting to collaborate with Nigel Mason, who is trying to do this network of networks in the space science. We were very successful with the EC projects. We got, over the last 20 years, we got more than 20 projects. Many of them we were coordinating, some of them we were just a part of this. So but I mean, EC project for us, it's crucial. They are very crucial, while they are almost like 40% of our budget, and roughly we get €1 million per year. And here you have some list of these EC projects. Now we are coordinating the radio block, which is almost €10 million projects for basically the development of cutting-edge technology development for the entire data chain. So basically from the receivers through data transport, correlation, data analysis, and then to ready data user products, right? Yes. And of course, we are also in OPTICON, but in ORP, but it's finishing in 5 months. And we are also in the ERIC forum. This is what we have been contributing with the ORP for the multi-facility call. So the call was basically, the main aim was to join the optical and radio infrastructure, so people could ask for observing time for at least, the requirement that you ask for 2 infrastructures, it could be 2 optical or 2 radio, or 1 optical and 1 radio. This was the minimum requirement. We had, within the ORP, we had more than 2,000 hours allocated for observations. However, only 340 hours were allocated, so basically 17%. And here you can see basically listed number of the titles of the proposals with the infrastructure that they have been asked. And then, so from 13 proposals, because 1 was withdrawn, 10 were accepted. And you can see also the distribution, which infrastructure they have been asked and allocated the observing time. I already mentioned about radio blocks. I think I can skip it. So basically, yes, we are working hard on this developments of the technical developments for the radio infrastructures, and we have more than 30 partners, and I hope today or tomorrow we will also sign the memorandum of understanding with Argos, which is the project that is developed here at Fort. We are also partner in the ACME, so this is a multi-wavelength, multi-aspect proposal. It's just started 1st of September. We will be delivering the transnational access, virtual access, but last but not least, again, also the center of expertise, because I mean, our Zsolt Paragi, he's the work package leader 3 to get to basically develop this expertise centers. We also, of course, we communicate and outreach, so we provided for the EVN and for Jive, and also for the other partners of Jive, and of course we are on social media, so yes, please follow us if you want to have the updates. Some future plans. We are also coordinating the GVA, which is Global VLBA Alliance, so basically, to make it short, you put together the VLBI arrays network on the global level, and this GVA then will talk to SKA how to organize the SKA VLBI observations, to kind of make it short. And of course, we have the science group, we have the decision body group, let's say, and also the technical group. Because we need to, of course, talk together. I mean, how do we organize this observation? How do we schedule them? How do you really prepare the tool for the call for proposal? So our aim is also, of course, to lead to this GVA. It's in the process. For the future, this year, I hope Thailand will join. We already have fringes with 2 dishes in Japan, Misuda and Usasa. We also got the fringes with Mercat, and I'm really waiting to tell you that, maybe, I don't know if next year, maybe in 2 years' time, there will be a call of proposal, which will be, like pre-SKA VLBI, because it will be EVN and Mercat. So we are waiting and working on that, and this would be really, really great step towards the SKA VLBI. Then, of course, well, we are collaborating with SKA and with NGVLA. There are a lot of developments going on also in Europe. So there is a proposition, British proposition to deploy 12 SKA meets. Okay, I'm finishing. There is also German proposition leverage for NGVLA dishes. And there is also Argos. And with Argos, we already have some work done because we think about smaller array of 6-meter dishes that they can be deployed in different either EVN station or as a new EVN stations. Of course, each of the solution, if you go to the SKA meat dish or to the smaller array of the dishes, you know, they have pros and cons, of course. And then, well, this I already mentioned, we really aim to be the node for the SKA VLBI. So we want to connect to SKA. And we will provide, of course, user support and service. And last and not least, we are also working to get the Ghana telescope in the EVN because we need to extend African VLBA network. You can imagine that there is Europe with many telescopes, and there is Africa. Not much really happening here, and then you have this very sensitive core in South Africa, in Karoo, where they deploy the SKA meat dishes. So basically, thank you. Stay tuned.
So, any comment, question? Yes, we have one. Vasilis, please.
Have you thought about how to address this? Yeah. Well, we are maybe we are not in a bad position because we have 2 areas. And indeed, I have heard that EC grants will require to have in the application either SP infrastructure or areas. But we still need to prepare the same. So we thought we could use sort of like salaries or permanent in the account for this question. Well, we can do it in I think we can also account a bit on the transactional axis, but we have the right to do it. Right? Because of the model that we are operating. Yeah. Because you actually do more because we are answering around on the same and of course on the transactional axis we will never pay 100%. It's just not allowed. So but we have to talk about the models and the cascading grants, yes, how to address it.
Thank you. So the next speaker is Marlijn Verkuter. That's gonna continue the topic of Jive in the terms of the EVN and TOM toolkit.
Exactly.
Yes.
Thank you. Good morning, everyone. The reason why me and my colleague Bob Alvin, who's still on there, why we're here is this project. And specifically within that project, there is a chapter which is called Seamless Performance, and that is a lot of things. But particularly this section is where we're involved in, and in short words, it means this, but that you can actually summarize it as this. This is what we're trying to achieve, make it available. So basically we want to move from, practically speaking, we want to move from this axis model to this one. And what you see is that it revolves around the central entity here, and within the European, within this project, that is the black hole, right? You know that. And our mission is to try to see if the facility, the European Field Network, that we can put that into this. Now, my name is Marlijn Verkuter. I work at the Proton Suite with the API, and our job is bringing, like Aga already mentioned, centimeter wavelength into TOM, or basically enabling VLBI access from TOM toolkit. We investigated that actually possible. Now, the EVN, in summary, is a worldwide network with a quite liberal interpretation of the word European, because we have facilities in South Africa, China, and Korea that are collaborating with us. So now with these formed baselines of about 8,000 kilometers, and if you do the math for centimeter wavelength astronomy, that means that the network can deliver angular resolution of about 2 milliarc seconds. Now, this is an image made at 7 centimeter wavelength with VLI network. And the image scale is about 100 by 100 milliarc seconds. Now, to put that into perspective, this is a single Subaru Hyper-Sprint pixel, 1 pixel at the same physical scale. So basically, what such a VLI network can bring to your science is quite unique. But before we get to this phase, that's actually going to be a bit difficult. Because, for example, one thing, the VLI network relies on extremely old software, 40-year-old software code that reads text files like this. Now, we already made in one of the previous projects, we made improvements, such by providing a Python wrapper around it, so that you can actually parameterize some of the values in these text files. But, yeah, so another thing that for this project, we've been actually working on a plugin for the toolkit. So that is a front-end module, and it's living inside a toolkit. And we're running then we created a backend running outside, where we have a database where you contain all the information about these observations. We integrated the EVM observation planner in that, but that provides all kinds of diagnostic plots beforehand that are essential to see if your VLBI observation, what those parameters of it are. And these data products, they are stored into the backend and made available in the front end as data products for the user. Another thing is we did integrate the Fortran code already in the backend. However, there are some snags, because one thing of interferometric array is that all the participating telescopes need to do the same thing at the same time. So for that, we've developed an availability tool, a web-based tool, where the participating web telescopes can self-administer their availability for the time ranges. And we integrated that availability tool in the backend as well. And it's coupled, the information in there is coupled to the front end in the POM plugin. So basically that when you want to submit an observation, you can do a quick check if all the stations that you need for your science case, whether they are actually available. And if they are, then you can easily submit the observation and it will be entered into the database. And afterwards, then the scheduling files can be downloaded by the participating stations. So, another snag is that within the European VLBI network, there is a time allocation committee, a program committee, that decides on allocating time, but also approving source lists. So, in order to address that sort of concern, we had to wrap the proposal database that contains some of the information. We wrap that with an ORP-based correction so that the EVM front-end module in the toolkit can actually communicate with the proposal database to verify that what you want to do, that it is acceptable. Now, when I said this, automatically generated schedules is maybe not as easy as that. Because, in fact, the calibration scheme for VLBI observation is essential to your success. And one of these things, the phase reference source cycle, this is quite often actually mentioned in the proposal, because this part is really critical. I've shown this plot in a different setting as well. But what we need to do, the extremely weak target sources are individually almost undetectable. So what you need to do is cycle between a calibrator source and your target source to track what the interferometer is doing. And based on this plot, I'll leave it up to your imagination to guess which color of the source, blue or red, which one is the calibrator source and which is the weak target source. So any automated form of scheduling that we would need to implement would have to basically find this category of other calibrators by itself without the use of dividers in principle. So just to give some insight into this, this is a typical schematic of an observation, and it shows the interferometric phase and amplitude over a period for 1 4-hour experiment. And what you can see in this experiment is observes only 2 target sources. And as you can see, there's quite a lot of calibration overhead involved. And for example, bandpass calibration, that was also one of the elements that we need to do. These plots are per telescope, and they have the amplitude, the response as function of frequency for each telescope individually, and they are basically the radio equivalent of these kind of filter shapes. Only they vary by telescope because, and over time, because people use different electronics, different backends at each of the individual telescopes. And there is finally this thing, another snack. Radio telescopes tend to be enormous amounts of metal, which means that if you try to remote control them, that is unlikely to go happen, because it's way too unsafe from somebody sitting here through a web interface and say, okay, let's move this 400 from infrastructure, and that it did without knowing if there's what's happening inside, right? So that is integration with the POM slightly more, makes it more difficult. So does this imply this? Well, hopefully not, because as Aga already mentioned in her talk also, earlier this year, the ORP pilot project opened a multi-facility call for proposals. And basically, that's addressing this part, that you submit a single proposal to a single process for multiple facilities in one go. And what we did, we looked at the results that we got from the call for proposals for those people requiring EVM or emerging, because they are both interferometric arrays, and they have share a lot of similarities in how you run or observe such experiment. And we asked ourselves this very question. Can we do this? And at a high level, it seems to me that most of the proposals in that call for proposal actually seem to be like this. You just point and see integrate until we have enough sensitivity. And there's that. And that is, they just use the plan ops, the observation planner. Say, okay, we need so many hours of observing to reach a sensitivity, so that's what we'll ask for. That seems doable. As for the calibration scheme, actually, we got quite a bit of mixed results. They went from not really specific to somewhat more specific to something being extremely specific about how to do these calibrations. Now, we could actually win a lot if we required this information to be part of the proposal. Another thing that we found is that, for example, for the emergings, that 2 out of the 4 requested a rather rapid response, and we believe that POM-based approach could actually be beneficial for such use cases. And then there's maybe things like the future, because we have created EVM frontend, which is basically just a plugin in the POM toolkit system. And it means that it's not unimaginable that you create multiple own instances that talk to our backend. And it would mean that we could possibly envisage that you have a specific own instance or an EVM-like array that is providing details that it knows about the array and helps the users to scheduling that. And another thing, like fast radio burst localization, there's people who have been using thousands of network hours. They need to do the scheduling by themselves. And the thing is that these fast radio bursts, they're happening 10 per day, but you have no idea where they happen. So there are people who are just looking and they catch one, and with the European field network, you can localize them to literally certain microarcsec and millisecond precision. For example, they could pinpoint the fast radio burst to within somewhere in the globular cluster. And it's maybe that we could help such science teams with this infrastructure as well. And then there's maybe other use cases for teams that we could help them with. And with that, I'd like to take it.
We're very precise on time, so yeah, congratulations. Any comments, questions?
Very dummy question we've been raising many times. Single dish flux measurements. Can you do that?
Yeah, but then you don't come to the EVM, because the EVM is the network.
Yeah.
And I've been thinking about that. Of course, we know a lot of telescopes.
Yeah.
But,
I don't.
but how they do the EVM is specifically, like Gaia explained, that is 3 periods per year where they collaborate. So what they do outside of that period is up to the telescope. And you would need to talk to the individual telescopes to get. And maybe there's something that could be improved. I agree. But for the EVM, that is out of their scope. I expect. Oh, more questions.
So Carolina.
It's already ready. This EDS participants
Yeah, it is integrated in Black Hole 2, right? It is.
It's not open, but it's there.
Yeah, and
not usable.
Not visible.
But again, so we needed to know what kind of things the multi-facility tool for proposals was also helpful there in trying to tell us what is it that the science community actually wants from the system. Because we have been doing this with scientists, usually prepare these schedules all by themselves with a little bit of help. And we rarely see, but in this case, we could have an option of looking at what people ask and see what can we do to automate that.
Any more questions? Maybe one short. David? Sorry, sorry.
I just wondered, why has it been possible to consider robotically controlling the telescopes? I didn't quite understand the mass aspect, if you have all of the protection, software protection.
No, well, it is exactly that. Very few of the facilities have their access control up to a level where you can delegate that to.
Okay, so it's just a lack of hardware at the moment.
It's immense what you need to do. We know from people in Germany, they've made an enormous steps there. But before you get it signed off by health and safety inspectors, that you really need to invest lots of time and effort. Because there's a reason why at most radio facilities, there's physical keys, there's an array of physical keys. And if you want to do something on the telescope, you need to take the key out and take it with you. And that as soon as one of the keys is taken, the whole facility is locked down. And there's a reason for it. Because you can really easily crush people in this thing. The telescope won't even notice. Yeah.
I'm afraid we are running out of time. If there are any more questions or comments, sorry, Simon, we can do it during the lunch break. Thank you, Marilyn. And then, yeah.
And the next speaker is Rachel Street, that's going to tell us about the EON Plus program, right? Yes, that's for laser. So, thank you. Because then they can also see you because we don't have a camera. So, guys, if you can.
How do I make this? That should do, right? Slideshow?
It should just be
Slideshow.
Yeah.
Right? That should work.
Perfect, thank you.
So hello everybody, and firstly thank you to the organisers for giving me this opportunity to tell you a bit about the AON network for those of you who may be unfamiliar with it, and also to tell you a little bit more about its latest incarnation, which is going forward. But before I go any further, allow me to thank the many people who contributed to this. Firstly at LCO and my colleagues sitting over there, but also at our partner observatories. Oops. So firstly, what is the purpose of AON? Well, AON is a collaboration of observatories designed to optimize all of the telescope operations and the user experience for time domain astronomy. This was driven by the goal of enabling follow-up for discovery alerts, but also in minimizing the disruption to observatory operations and the workload on the staff, given that those are finite quantities, as we all know. But in order to accomplish the science we want to do, we need to have flexible scheduling modes and very responsive telescope operations. And in order to enable that, software is a vital component. This was really driven in the United States by an awareness of the imminent start of the Rubin Observatory's Legacy Survey of Space and Time, or LSST. Some time ago, back in 2016, Nagita et al. Did a detailed study of the kind of telescope facilities that was going to be needed to follow up the discovery alerts from LSST and thereby realize the science by characterizing them. This table has stuck with me ever since, and you'll see that it highlights the need for a range of telescope apertures, a wide range of instrumentation, and this is true for following up almost all of the science that we want to do with the network. It also highlighted the need for a distributed network of telescopes as being the maximum responsive capability for something that may be very quick transient. And so the AON network looked at what we wanted to do and looked at the equipment that we have available and said, okay, what is the most minimally invasive thing we can do to enable the science we want to do? And we came up with two major capabilities that are necessary to achieve it. One is you need a much more flexible way of scheduling observations. It needs to be responsive to when the science needs to be done, not when the TAC has convenient time. That is ideally optimized with software tools to make it reactive. The other is that you as a user, as a scientist, need to be able to send your observation request to the telescope for execution. So, the first up, the dynamic scheduling, as we've heard from previous speakers. If you operate in a queue schedule mode, by which I mean observatory staff make sure the operations are conducted, that is extremely flexible and allows observations over many different timescales. Dynamic queue scheduling, usually enabled by software for the sake of speed and workload, enables that to happen on a rapid change. Now, there are many examples of this. The Liverpool telescope in particular was a leader in this field for some time. Gemini LCO itself, the Zwicky transient facility, and a number of other facilities have this kind of dynamic queue scheduling available. The other one I mentioned was programmatic access, and this simply involves a user interface where an astronomer can request the observation that they want to do. That portal can provide traceability, and it then enables the staff and the user to monitor the progress of that operation as it continues. And all of that can be enabled just by having APIs which users can communicate with the observatory. The advantage of that being programmatically accessible is that then you not just do it through a user interaction, you can also do it through a TOM system, which allows a lot of this to be automated and thereby much more responsive. And so the architecture of the original AON network looked like this. You have the SOAR, Gemini, and LCO telescope facilities operating in part. It's not entirely AON mode all of the time. That's not a requirement. LCO and Gemini are Q-scheduled all the time by virtue of their operational model, but the SOAR telescope was not. The SOAR telescope chose to use the LCO user portal and scheduling system rather than develop their own. But Gemini, by contrast, had their own software, so they chose to continue the operational model. But SOAR remains a manually operated telescope. There are people on the summit every night making sure that telescope operates. And so that's an entirely viable model for an AON-compatible telescope. All of these tools are made programmably accessible through primarily the TOM toolkit, but that's also accessible to any other Marshall system, such as Sky Portal. Oh, no, come back. Okay. One thing I did want to highlight is some new software that we have made available from LCO. I've said already that we make no changes to the telescope's operation software, that's the telescope control system. All of AON's software sits above that. And one of those things is the user portal, the telescope scheduler, and various other components. That can be an overhead on the observatory to put together. So what we did with the help of the Heising-Simons Foundation is we made available LCO's own software repackaged to operate independently, so that this can be applied at any observatory to operate standalone. It includes both an online portal for users to request observations, the configuration database. It has a built-in adaptive scheduler, if that's what the observatory wants to do. And it also provides tools such as the downtime database and an online science data archive. And because we developed this software in parallel with the TOM toolkit, it is fully AON and TOM compatible out of the box. So, from its original start with the 3 founding facilities, AON has expanded with a number of compatible facilities that we have worked with over time to usually work with their own infrastructure and make it compatible with the TOM toolkit. A shout out particularly to the innovative work at SAAO through the Intelligent Observatory. Liverpool Telescope I already highlighted. We've also been working with the Neil Gehrels Space Telescope. Their team recently provided an API that allows users to submit targeted opportunity requests to the spacecraft. So we have a TOM plugin for that as well. And we're currently working on a plugin to the new ESO portal for all of the ESO telescope facilities. There's a couple of other facilities that are worth mentioning that are work in progress. One is the Blanco 4-meter telescope, which we are currently working to bring the new firm instrument into AON. And we're also working with the Rubin in-kind telescope facilities. So that's the current status. We have been in operation for several years now, and in the case of SOAR especially, where they went from a purely manual operational model, they have seen increasing proposal usership of people actively asking for AON mode operations over that period of time. The network is primarily optical, with the exception of SWIFT that covers the UV and X-ray. And we have been working closely in collaboration with the OPTICON-RadioNET pilot program, which you just heard from Magellan already. The limitations of this is that several of the major facilities, especially from the US community, have not yet been integrated. And we were somewhat limited in the wavelength range that we cover so far. So we were looking for opportunities to expand our capabilities. And that came across as of last year in a new program from the NSF called Windows on the Universe. This was an opportunity particularly aimed at time domain and multi-messenger astrophysics, and it really focused on the ability to observe across wavelength boundaries. And so this was a really good opportunity for us to try and expand the AON network, and so the AON Plus program was born. So the first thing we wanted to do is bring in some of the other big telescopes in the US complement, or the US adjacent complement. This is, first of all, the Canada, France, Hawaii telescope, 3.6 meter on Mauna Kea. This brings in more optical and infrared instrumentation, including wide field imaging. They have developed their Koalahu API system for receiving observer requests already. And as part of this program, we're going to expand the API that it offers to include all of the instrumentation. And we're going to develop with them the capability to submit rapid TOO in under 24 hours response. The next up are the Keck telescopes, the twin 10-meter telescopes also on Hawaii. They have also recently announced a new API for their operating system. And they have, one of their project scientists has been working on a TOM toolkit plugin for this, which we will bring into the core toolkit as part of this program. Whoops. Sorry, that was rather sensitive. Okay. We're also partnering with colleagues at the University of North Carolina, who are the central hub for the Skynet telescope network. This is a network of 20 observatories. They're all coordinated from a central user portal that already offered API capabilities. And what's interesting about this one is it offers not just optical, but also radio facilities, and therefore completes our wavelength bands. So we are partnering with them, and we will be building a TOM plugin to allow users to submit observations to that network. And lastly, but by no means least, we have partnered with the US National Radio Astronomical Observatory. This organization is the equivalent of the National Optical and Infrared Laboratory for radio telescopes, and it operates all of the US major radio facilities, including ALMA, the NGVLA, Green Bank Telescope, and more. They have a portal of their own, so once again, they have a distinctive system, but they are interested in developing API communication with it. So we're going to be working with them over the next 3 years to develop TOM toolkit plugins that will enable users to request observations through that system. And so the AON Plus network is not just building about building new capabilities at telescopes. One thing we wanted to do was to make this more broadly accessible to the community. And so what we're going to do is, rather than have everything necessarily embedded in the TOM toolkit, we're going to have an AON Plus standalone library, which will work very closely with the TOM toolkit and will be nested within it, but can also be used as a standalone library. And that enables people to plug it into all sorts of other software and portal opportunities that they're developing. So it allows a lot of developer flexibility in that respect. And the other component of this is to build a community around observatory network operations. And this starts off by, we're going to be hosting annual workshops for telescope operators. This is for the operations staff to bring operations staff together and exchange experience, exchange tools. And we also have a visiting developer program. So this is for us to be able to bring people to LCO headquarters for a period of time to work directly with our staff. And we found that to be a really productive mode of collaboration. And so I will leave you with this summary slide. If you have any questions, please do talk to myself. Lindy and Joey are over there in the corner. We can answer any questions you have. And we have lots of online documentation as well. So I will stop there. Thank you for your time.
very much, Rachel. Any questions? Comments? Simon.
Yeah, that's all my questions. So this is really amazing. It's really amazing.
Thank you.
So we heard we heard in the last talk that the source lists get approved, and the observing strategies need to not be you have to, so are you going to have any controls to make sure it's, for example, if it's observing in infrared using detectors, that you need to have calibrations of a certain style, that happens to well, or can you find out with unreasonable observations?
So we don't impose that at the Aeon level. What we do is when we build a plugin for the toolkit to request observations is we build in validation. And we generally work with the participating observatory that their API has some validation on all of the fields that you submit. So if you have to have a certain calibration schema, for example, and it's not in the request should not be validated.
So at that level,
Yeah.
validation rather
Yeah, exactly.
more stress.
Yes, but it does take some of this, it takes some of the mistakes out of it if you do validation at that level, because then anything that does get through, both the operations staff and the user know that it's valid. It's worth putting the time in there.
It's impressive. I was just surprised to see that Tech actually wants to do.
Yes.
They were they didn't figure out what their motivation is because they didn't even want to publicize what they are observing every night, let alone use someone else's software.
I think it really comes down to a growing awareness in the US that time domain and multi-messenger astrophysics are in the US Decadal Survey. They are the major topics, and over the course of the next decade, they are going to be where, dare I say it, the lion's share of US science is going to be focused, certainly in astronomy. So I think the observatories looked at that and realized what their users are going to want to do. And so they were increasingly hearing from Noir Lab, and in fact, they have some staff who are now at Keck. We used to be at Noir Lab and somewhat took the Aeon ethos with them. So.
I think we can thanks Rachel again and move to the next topic. And the next talk will be delivered by Rupak Roy, who is there online with us, and that's the last talk before the lunch break. And the title of the talk is an automated tool to find the UV transients and its inclusion in BHTOM system. So Rupak, we can see you, we can hear you. I hope you can hear us.
We don't see your screen.
But we don't see your screen. Can you share your screen?
Yeah, I will share the screen. Share screen. So what to do?
Green button in Zoom. Oh, yeah.
Yes. Now we can see the number of slides that you have. Just a reminder, you have 25 minutes.
Yeah. Start?
Yes, you can do the full screen mode, I guess. Yes. And now we can see you well.
Yeah.
And okay, thank you.
Yeah, thank you. Thank you for giving me this opportunity. Sorry, this time I could not be there because of some funding issue. It starts from the last year when we visited. I visited this Malta conference. There was a discussion with the Lucas that whether we can include the UV data within the BHTOM or not, because there is a huge archive from the Swift itself. So all started from there, and I had developed a tool which is nothing new, but that actually give a very quick output of UV, particularly based on the SWIFT data. So, for example, I have borrowed this figure from one of the Luca's previous documentation from the BH-DOM documentation. So you can see that there is a huge data available in optical and IR. And this information, if you can extend it to the UV as well, using the SWIFT archive, it will be very useful for the community. And particularly, it is useful because many transients like supernova and others, novae, sometimes shows particularly outburst even before the actual eruptions or actual explosions. So those outbursts may sometimes come in the form of a UV. So also the archival data is also important, and in some cases when we have the actual UV follow-up at that time, then using this onboard tool, we can do the simultaneously the UV photometry as well. So just for completeness, here is the SWIFT observatory, and we are talking about this small telescopes, which is UVOT, and this is the optical layout of this UVOT telescopes, and it's a very fantastic instrument, and gave I would say a big data set over last many years. And here is a much more detailed about the SWIFT UVOT systems, and particularly the filter systems. And here we are looking for this 6 particular UV data sets, UV filtered data. For example, this UVW2, UVM2, UVW1, and UB and V. Out of this, B and V are in optical window, and the others are in the UV. So, what is the new thing in this pipeline? So this pipeline is not new. This is based on basically the HIASoft, which is wrapped within with Python. And there are other codes. Individual people have developed their own codes for like this also. And there are particularly codes like DRESS code, which use for the data reduction of the extended sources in UV. However, here are some results from this code, particularly about which I'm interested to talk. So it shows some confidence that this gives a very good results. So these are two events which are nuclear transients. So 2018 DYB was a tidal disruption events, and whereas 2020 OHL is a nuclear transient which may not be an origin, may not be a tidal disruption event. Rather, we propose an object which is created due to the fluctuation of the disk. So this all happened because of the very good UV photometry we were able to do using this software. So there is another example which is not nuclear transients, rather it is these are two supernovas. So one is superluminous supernova SN 2018 BSZ, and another is type 1c supernova 2020 ACAT. So for these objects also we use this particular tool, and this worked very well. So in general, the SWIFT and UVOT systems have some common pipelines, as all of you know. That in the left-hand side, you can see there is the general SWIFT pipeline tools. So it gives the level 1 data after getting the telemetric data from the instrument itself. It corrects for the two different type of processing. One is event data when the object is very bright, and there is the imaging data, and in both cases it does the calibrations during the level 1 itself. Then after the level 1, it goes to the level 2, where it gives the data goes for the coordinate transformation and all these things done. And finally, it gives the level 3 data, which gives some sort of product. But this product, I will show you the little bit different from what the product we need. For example, in the right-hand side, it is the UVOT pipelines, particularly which use the UVOT IMSUM, but I also want to emphasize that UVOT has also GRISM. So there are GRISM data also available from the UVOT. However, for this particular work, I have concentrated only on the imaging part of this data. And UVOT IMSUMs gives the summation of the images, and it's the sum data, and then it's detect the sources in the UVOT image. And then further, by the source, UVOT source, we used to get the using the 0 point, we get the magnitudes of on the fluxes of the particular target source. So this is typical UVOT pipelines, and these are the typical files that we know. And some of them here, what I want to emphasize that what the UVOT product is given is actually, this is the sky image and the exposure map images, which are basically co-adding of all types of data available. So here probably we don't have the information about the individual filters. So this is one of the area what this particular tools works. It takes the data products, it uses the Swift YASOF tool, but it on the top of that there is a Python wrapper which automatically download the level 2 data. And if this is the total observing time of a given epoch or given observation ID, which may be consisted of different orbits. So there are maybe orbit 1, orbit 2, there is orbit n up to we can go. Similarly, there are exposure maps for that. So with this particular tool actually goes for the first checks for the correction, whether there is astrometric correction is correctly done or not. If it is not there, then it use the USNOB catalog to do the astrometric corrections, and after that we get both the astrometric corrected sky as well as astrometric corrected exposure map. And from that we actually get the summed sky map as well as the summed exposure map using both UVOT. In both cases we use the UVOT IMSUM. So far these things are more or less same, but after that that's a little different. For example, we use the UVOT detect using these two things, and we get the source catalog. And similarly, using these two same information, we can go through this UVOT source, and we get different informations of the source of the particular target in UW2, UM2, UW1, and UBV bands. So these are the in this particular tool, it gives in this way for a given epoch at different at different wavelength or at different bands, what are the magnitude or the fluxes. Now this Python wrapper runs for the this above task runs over each epoch in a loop, and finally it can produce a light curve for this target. And this everything it does automatically. So here I have shown basically a summed image of UVOT sky map, and as well as the summed image of UVOT exposure map. So using these two, we can finally get some sort of light curve, which is ready to publish in the form, the data. And it gives the output in two forms. So one is as a light curve, and another is as a table form, where you can see that the first column is basically your observation ID, second column comes as a JD, and the third column as a band information. Then here I have shown it the AV magnitude and the error associated with the AV magnitudes. In some cases, we used usually get the non-detection. In those cases, in my code, it gives as an upper limit as a 999.0 to show that the corresponding magnitude is basically the upper limit. So in this way, it can give you a final product of an UVOT. And particularly here, I have worked on the image data, and but this data comes in the form of the main code gives it in the form of a data cube. For example, it comes as in one axis if it is the time axis, and another axis is magnitude or flux, and another axis is a band or wavelength. So it comes in the form of a data cube. So either it can be stored in a FITS format so that you can get the data directly from there and by slicing that particular FITS, and or it can be stored as a JSON form so that you can fetch the data of a particular day, or if you want to find out the ACD of a particular epoch, that you can do from this cube, from this data cube. However, I would also like to say there are issues with the UVOT PSF. In the default UVOT PSFs the default UVOT PSFs are based on the curve of growth as shown here, and its PSF is roughly, the radius is roughly 2.5 arcsecond, and normally we usually take a 5 arcsecond default radius where extracting the source point. However, there are problems if this is particularly a region which is very crowded, or if the background is very dense and or actually very luminous. So in those cases, if we use the smaller aperture, that can make a better signal to noise ratio, and your source estimation of the source flux as well as the magnitude is much better. And actually, UVOT source uses the aperture radius of 5 arcsecond by default, and if you UVOT aperture correction none is used, then it will use the 5 arcsecond aperture. On the other hand, you can use a smaller aperture for using this aperture correction table. So UVOT also provides this aperture correction table, which is actually embedded within the Gaia tool itself. And for example, in most of my work, I prefer to take either 3 arcsecond or 3.5 arcsecond aperture, and with this aperture correction terms are used. However, nowadays there is a problem with the Swift UVOT aperture corrections. These numbers may not be very exactly correct, so there may be a problem in very high precision photometry. So in those cases, it is essential to find out the actual PSF of the UVOT sources, and that may be a good project to see. And here is one example where I have shown that the field of AT2020 OHL, which the light curve I had shown earlier. Here you can see if you use the 5 arcsecond aperture, you are getting a little larger flux. The object becomes a little brighter, and it is mostly because you are calculating the flux at the center, where you can with 5 arcsecond there is a high chance that you will get something beyond the source. You will basically calculate the galaxy center as well, the flux from the galaxy center as well. So we use the 3.5 arcsecond aperture for this particular cases and showed that this is the best estimation of the flux for this transit. So there are issues, still there are issues, and and one of them, as I said, this is the determination of the better PSF. What I think is need to be done there are better astrometric solutions we can be worked on. I mean, in this particular direction we can work on. And there is, I still did not work on this, the storage of the data in the form of a FITS or JSON form. That is one of the things that may be useful if we want to include in the BHTOM environment. And another thing which I'm quite interested, recently I found this particular paper that there is a possibility to compute the photometry of the saturated target also. So these are few things which I look forward to work on these particular things. But at the same time, I am now I'm quite interested now to give a small demo about how this code works. So I'm coming back to my main. I'm escaping from this my presentation mode. So here I have kept. Probably you can see, right, my terminal. Hello. Hello. Can you see my terminal? Yeah.
Yes, we do see your terminal.
So I just kept few files, few folders which I have only download from the Swift archive. And as I said, this particular code, which is this Python code and works on based on the Airsoft, this particular code gives in the cubic form of data, and it is actually called by another code which I have written is as a demo.py. So this code actually takes the three things. One is your region file around the OT. Region file is the background, which is I have taken as a 50 arcsecond radius background, and this is I say that this is what is the sigma 3 sigma detection level. This has been mentioned. So if I run this code, and I will just be interested to take a few questions during that time. So so let us see what does it produce. So it start to work on, and maybe I will be happy to take some questions during this time. It will produce some results. It will show you some light curve. So at this moment, it is going through each and every folders automatically. And to make the things faster, I did not ask the tool to download the data from UVOT archive. And so I just kept the data there. Maybe in the actual case, it can download the data online. Yeah. So I'll be happy to take some questions if you have. Meanwhile, it will come up as some output.
Yes.
So do we have any questions? Yes, we have. You can speak loud, Nada.
I hope you can hear me. So I have a few questions about this code.
I cannot hear Nada. Can you please?
Yeah. Sorry, I will come here. Really amazing work. So I assume there's the pre-requirement to use this because you need to install Airsoft, right?
Yes, Airsoft should be installed and few Python version, Python dependent.
Okay. Do you have this? Is it already accessible? Is it public, or are you only using this by yourself?
Yet not make it public. So I was interested to make it public through BHTOM. So that's why I talked to Lucas last year, and we had a discussion, right? I mean, at the time. So
yeah, I would be really interested in trying this because
I just took 5 days data so that it can come quickly, and so you just there is a possibility that you just have to give the array deck and your how much pixel this radius of your source radius, you just have to mention. Then it will automatically calculate the correct background location and all those things. But that part of the code I did not show here because it will take more time. I just showed that there is another option when you have your own region files. You have your own background region files. You have, so this is now your this light curve is ready for this particular for set data. Okay. Yeah. So this is light curve, and along with that, as I said, it will give you a data output. So you can see here all data. So this is again, as I said in the previously. So this is your observation IDs. Then these are your JD. Then these are the filter information. Then your magnitude and magnitude errors. So this magnitude errors is just I have to just work out with that. So this is just I can make it 2 decimal place. It is actually I mean I have to correct it. So now it is a long number which has exactly no meaning this much. So maybe 2 to 3 decimal is fine. Yeah, so thank you. I mean, if you have some more questions, I will be.
Thank you very much. That's amazing work, Rupak. Do we have more questions or comments? Everything, yeah, thank you. I guess you could hear the clapping. So thank you for the presentation and demonstration of the code. And we are approaching the lunch break. The lunch breaks are outside. Thank you, Rupak, and feel invited to lunch as well. And we meet here
10 past 2, so that we have full 1.5 hours, okay? I will keep the Zoom running here, just in case, you know, to keep all this streaming online, but we say goodbye for now. Thank you. Now it should work.
Welcome, everybody.
That is okay.
Welcome online. I hope you can hear us. We're ready to go, and I think we are. I think we have 30 seconds.
Can I quickly go through, because I think the
wanna
rendering
check?
is
This is not a high-speed version of the talk, it's a test.
so done. Thank you very much.
You happy?
Yeah, not super happy with that. Anyways, it's fine.
Okay. So we're going to start with John Antoniadis. Apologies if I'm pronouncing it wrong.
Oh, well, that was perfect.
And you've got 25 minutes to tell us all about artists.
So, thank you very much, and welcome to this after-lunch talk. I hope I won't bore you too much. So my name is John Antoniadis. I'm a researcher here at the Institute of Astrophysics, 4. For the next 20 minutes or so, I'll say a few things about the project that we are running here called Argos. This is a project aimed to build a wide field radio facility here in Crete. So first things first, so what Argos stands for, it's the array for gigahertz observations. So this is not a very suggestive name, but what this really means for us is that it's a telescope that combines broad frequency coverage, wide field, high sensitivity, and high resolution at gigahertz frequencies, and at a low cost, so that's very important for us. But also, it is a facility that can produce science-ready data with low latency, so it's a public survey experiment rather than a telescope facility. So this is how the concept started. So we're talking about an instrument that has a very large collective area, something like equivalent of to a Arecibo or SKA 1 mid. But that sensitivity is built up from using small 6-meter parabolic antennas deployed over 4-kilometer baselines. And because of that, because of the small antennas, the instrument also has a large field of view. And because of the large baselines, it also has, oops, I didn't break anything. It also has a large resolution. So the frequency range, so it's a single frequency window, 1 to 3 gigahertz. It's being designed using ambient temperature electronics, so no need for cooling. So that makes it also very cost effective. And what else is important here? And also able to track elevation and azimuth. So why do we want to pursue this design? So there are a few advantages. First of all, it's low cost because the antennas are very small, so you can just buy them off the shelf. There are many companies that build this type of antennas for space communications. It's also scalable, so you don't have to build the entire thing in one go. You can just keep adding antennas as funding comes in. So the way it is being designed is also expandable and modular, meaning that you basically have 1 or 2 basic data streams, and then you have science pipelines that subscribe to these data streams that work independently from one another, and they can process the data in different ways. So I will talk about this more later on. It's also complementary to other facilities. We don't have any wide field radio facility in Europe or anywhere else in the world. It's something that is becoming obvious that is going to be needed in this era of time domain multi-messenger era that we're entering. Yeah, as I said, there's also some legacy value because it's a public survey instrument, so there's science-ready data that are being produced. So the main science themes, they're mostly all related to time domain and astronomy and compact objects. So just to give you some examples, very quickly. So fast radio bursts have large collecting area, large field of view, and good resolution, and that makes the instrument a perfect
a survey instrument for fast radio bursts. So we're currently designing a commensal mode pipeline that will be operating all the time. And when the instrument is operating in the so-called subarray mode, so we have 4 subarrays working independently from one another, we expect one well-localized fast radio burst per hour. What's also important here is not just the total number of new discoveries, but it's also important that the instrument will be sensitive to high redshift fast radio bursts because of the frequency coverage. So being able to localize high redshift fast radio bursts is important if you want to use them for cosmology, dark matter searches, microlensing, and so on. So another big thing for us is pulsars. So there's approximately 1 pulsar per square degree on the sky. So having a large field of view means that you can observe a few tens of them at any time. So this is a big part of the science operation is going to be devoted to pulsar timing. So monitoring pulsars. So things that we plan to do is timing using coherent dispersion to maximize the signal to noise. And the science products will include sub-banded times of arrival, flux polarization information, dispersion measure information, rotation measure, and so on and so forth, and also some imaging as well. So this type of capability is important if you want to do population studies, study fluxes, discover glitches, and so on and so forth. Another big thing related to pulsars is pulsar timing arrays. So about a year ago, there were 3 major collaborations. In Europe, we have the European Pulsar Timing Array. There's the Nanograph in North America, the Park Pulsar Timing Array, and also the Chinese Pulsar Timing Array. And we all announced evidence of a low-frequency stochastic gravitational wave background that was discovered using monitoring of millisecond pulsars across the sky over many decades. So basically, using this technique, you can use these pulsars as a galactic scale gravitational wave detector to detect low-frequency gravitational waves, and we are beginning to see the first evidence of this in our data. So moving forward, what is becoming obvious because of these discoveries is it is going to be very important to expand the frequency range of these experiments to higher frequencies. So this blue line here shows the current sensitivity of the International Pulsar Timing Array, which is the consortium of this consortium. So the current sensitivity, and this line here is what we think we saw, the stochastic gravitational wave background. So with Argos is going to contribute to this type of experiments in 3 ways. It's going to increase the sensitivity in 3 ways. So first of all, because it will produce broadband times of arrival, and it will also have the capability of monitoring profile changes. This will be very important for characterizing what we can call timing noise in the data, that is hindering the correct characterization of the gravitational wave pattern. Second, just because we will produce a very large number of new times of arrival, it will increase the sensitivity, but what's most important perhaps is this: we plan to do high cadence observations, basically daily observations of pulsars. So this will expand the sensitivity to microhertz frequencies, and as you see here, this is very important if you want to characterize the different contributions to the because the different types of contributions, so things like the black hole background, cosmic waves, these things are expected to be most different. And it's also important if you want to do multi-messenger astronomy, if you want to see single sources, and then follow up optical or other wavelengths, because the louder sources are expected to have relatively short periods. So there are at least 2 known candidates that will fall within this sensitivity. Imaging, image plane transients, again, a very big part of the science that Argos will be doing. So what we want to do, the ambition is to do a high cadence full Stokes imaging of about 500 square degrees per day, and also to produce light curves and transit alerts, and also follow-up figures. So it's, we want to do this basically for things with variability that vary in time scales from a few minutes, so things like pulsars, pulse ellipses, short earlier, to things that have variability time scales of a few years even, so things like microelectrons. Another thing that became important to us very recently, so it was not in the initial requirements for the instrument, is wide field VLBI. So this is something that became obvious to us as very important for the community. So now we design Argos to be fully linear graphical. That's in the requirements now. So Argos, simply by having a high sensitivity instrument, Crete, for instance, that will improve the UV coverage sensitivity, especially with sharpened targets or SK-related targets. So that's important. But also, as Ada mentioned in her talk, we now started to develop this concept of being able to deploy smaller parts of the array, so small Argos substations across Europe to build up a wide field VLBIs. So something like local. So with the project that is currently ongoing, we hope to test this capability, and a recent development is that we recently secured some extra funding to buy a major clock, which is nice. So we're going to have a major clock here, and we're going to be able to do some of these VLBI experiments with the Pathfinder. So just to say a few things about the current project. So that was funded through the European Commission, InfraDev design study. So there are 4 institutes involved. Fourth, we have Institute of Astrophysics and the Institute of Computer Science that is in this building. We have the Max Planck Institute for Radio Astronomy, CA in Paris, and the University of Piraeus in Athens. So the design study, so the timeline looks something like this. So we're currently gearing up towards the preliminary design review of the instrument, and the final deliverables will be a fully working 5D prototype and a critical design review with an approved fully costed design. So this is just an overview of the structure of the project, the different subsystems that are being developed. Skip that. Say a few things about the current status. So front end and the feeds. So the front end, the DCs for the prototype are just off the shelf. We bought them from a Chinese company called Antesky. And the turnheads and the mounts are being developed by a company in the UK called Poam Electronics. They're currently undergoing factory acceptance testing. The feeds are fully digital. So what this is a custom design developed by Max Planck and the University of Piraeus, and they're based on this low ambient noise LNAs, and also fully digital, meaning that the sampling and digitization is happening very close to the feed. The fabrication of the feeds is also interesting. Obviously, if you want to build an instrument with 1,000 feeds, then things will be breaking 1,000 times more frequently. So you want something that is both cost-effective and durable. So what we're currently testing is this 3D printing technique. So we basically print the feeds in plastic, and then they're nickel coated, and then on top of that there's an additional plastic layer for weatherproofing. So currently we have the first feed that is undergoing factory acceptance test, and it's looking very good. So that's okay, let me skip that. The backend and the correlator is being developed by Machine for radio astronomy. The beamformer and the correlator are basically copies of what the Max Planck has built for the Mirka telescope. But as I said, one component of that is that we do these are digital feeds, so we do the sampling very close to the feeds using FPGA. So currently for the prototyping, we use these RF sock boards that are built by Real Digital. There are four main streams, data streams that are coming out from this instrument: the VLBI, spectroscopy, pulsar search, and pulsar timing. And currently, within the framework of this project, we are developing 4+1 pipelines for image reconstruction, transient detection, pulsar processing, and FRB processing. Last but not least, as I said, we actually want to deploy this instrument here in Crete. So we have a very good candidate site that is, are we actually going to see this? Okay. So for those of you that are going to Skinnacas, this site is actually visible from Skinnacas. It's further down. It's a nice plateau that is very radio quiet. So we did some. It's actually the birthplace of Zeus. He was actually what? It's a different story. So he was actually supposed to. He grew up in this game. So it's decent. Very radio quiet as a European site can be. So now the next step is to actually get some permits to deploy some of the antennas there to test the environment. Okay, so that concludes my talk. If you're interested in this instrument, feel free to talk to me and all of us. So thank you very much.
Keeping very well. Do we have any questions? How do I see if there are questions online?
I have a quick one because we started then talking about the zero strike. When do you expect the first flight?
For the Pathfinder?
Yes.
So we did have some delays, but all the equipment is currently on the way.
Oh, okay.
So I have to leave in a few minutes to go meet the constructor for the ground. So very soon, hopefully. Yeah. It's not first light, but you know.
Yes, but at least
actually things are actually happening. Yeah.
I have a question about the site, and you're keen for people to come in and adopt an antenna, which could be purchasing more antennas, presumably. Do you have infinite capacity to put more antennas there, or?
Actually, currently if I have to be honest, currently there is zero capacity for zero antennas. So, but the plan is, one way forward would be this concept of breaking up the instrument to substations that can be deployed across Europe. Actually, increase the baselines by 2 orders of magnitude, basically, and that may make it easier to build up the sensitivity to full sensitivity.
Regarding substation, is it going to be a single antenna or you need more?
No, the idea would be that the substation would be like a subarray, so a few tens of antennas, let's say.
How many?
So things like, 15 to 16 6-meter antennas are equivalent to, a 27-meter telescope. So that's like a typical, VLBI station, let's say. Yeah.
How will the performance compare to, say, Meerkat or SKA MIT, or for that matter?
So that's a very good question. One of the main motivations for developing this instrument is to do SKA follow-up. Obviously SKA will have a huge sensitivity, but we will never be able to follow up all the things that we discover. So we need, then it becomes a bit like a Ponzi scheme. Like if you want to beat another SKA to follow up SKA, and then you need something else. But this is this is why I think it's important to develop this kind of concepts, because these are cheap. You can build an instrument with a sensitivity of escape with just 1% of the cost.
It would be excellent for radio frequencies.
Yes, exactly.
Oh, one more from that.
What are you planning? I mean, how is it going to be a survey? Are you going to scan, or it's the people? I mean, would it be possible to apply for time, or do you have the plan already?
No, so the main idea is we have to think about this, but the main idea is to, most of the time we'll go to public surveys. So things like daily monitoring of specific list of pulsars, following up transients, and then doing imaging surveys. Yeah, but then there will be some also possibility to use the instrument for open time.
Lovely. Thank you very much. I can't see if there are questions online.
I did check.
So now it's Carolina. Hi, Carolina. So you've managed a holy grail of getting simultaneous optical and radio monitoring of
Yes.
AM HERT.
Yes.
And so
At least a little bit. Not that wonderful as we expected to, but
We'll see.
still.
This place, the best place to stay is here.
yeah, stand
Okay.
there so they can see you and hear
Okay.
you online. And I'll go like that when you have 5 minutes left.
Of
your
course.
15 minutes.
Of course.
Try and save some for questions.
Of course. Thank you very much. I'm an optical astronomer. So until this project, my only contact with radio astronomy was taking nice selfies under the radio dish. So what I can confirm is what Agnieszka and Marjolein told you, that EVN pages are really user-friendly, because when I was preparing my first EVN proposal, it was really helpful, and the guidance there is really excellent. So I really recommend you, if you have any doubts and afraid that you don't know much about astronomy, radio astronomy, you still manage, really, believe me. I will tell you a little bit about very well-known polar AM Hercules. Strong magnetic field prevents to create. There is a pointer. Okay, no, okay. That prevents to create an accretion disk and force the stream to go. Okay, with here. I will manage, yeah. It is not like very crucial here. Prevents to create an accretion disk and force the stream to go into accretion columns onto the white dwarf. It leads to the gravitational, to release the gravitational energy, which we see as a cyclotron emission visible in optical, radio, and ultraviolet bands. And the problem with systems like this is that we have like completely distinct separate sets of observations. Like, for example, beautiful decades of optical coverage by AAV, so observers, beautiful over 30 years of radio observations recently published in a really nice paper, completely separate. Nobody tried to meet these data sets, try to investigate it together. So I decided to, with Marcin Gawroński and Krzysztof Goździewski from my institute, we joined forces as an optical radio astronomer and specialist in astrometry to have a project which tried to explain the processes in this type of stars, because we see the low and high states like in optical bands on the upper panel. We sometimes see some kind of changes in the radio flux like presented here, but we actually do not understand the phenomenon. We have some hypotheses that, for example, cyclotron emission from the jet is the explanation from the radio emission, or maybe electron maser emission near the white dwarf or the secondary, but still we do not understand the process.
So the first attempt was done over a decade ago by Marcin. He had 6 epoch of radio observations done by European VLBI network from December 2012 to December 2013, made in the frequency of 5 gigahertz. 8 antennas was used, the biggest in Effelsberg, also the one in Torun was included. And these 6 epochs are marked by the arrows with the A, B to E, F letters. And these light curves from VSO archives, as you can see, they catch the star during the decline from the high state and observe then only during the low state. Also, the coverage in optical band was not like excellent one, so the analysis at that time was made basically on the radio observations. What Krzysztof Goździewski did was an excellent work in astrometry because they managed to calculate the precise parallax and distance for the system using also the archival observations, not only the recent one that at the time Marcin gathered. So the distance was 88 parsecs, and formally it is still the most precise one for this system. And this 6 epoch you can see here. The red one is another object, but the AM Hercules is visible on the 6 panels. No huge changes in the radio flux, nothing seriously important is happening here, but no optical data for the same moment made it impossible to investigate it closer, whether there is any optical radio dependence for the behavior for the system. And what we decided to do in this panel, you can see the light curve from another paper which was recently published for 2 polars. And in the upper one, the gray dots, then overlapping with the blue one, are the consecutive many test sector excellent quality for excellent quality light curves. And we decided that because for this system there are 3 subsequent sectors scheduled for June, August this year, that we will apply for EVN radio observation. At that, with that approach, we will have like 2-minute cadence undisturbed observation from test satellite in optical band, and we will have a good EVN session. So I applied for this session. I can assure you it wasn't that complicated. This time we had like 10 dish. Additionally, from the 8 previously mentioned antennas, the Latvia, Ibene, and Sardinia dish was participating, and the observations were scheduled for the 18th on June this year, 6 hours in total of time. And this is the light curve of from TESS, 3 subsequent sectors as they promised, starting in May, ending in August. So you see that really recently very fresh data. By this black arrow is marked the area where the 18th of June happened. At that first moment, we were scared that it is on the area where one sector ended and the second one started, but what we noticed is that we were lucky this time, and great optical observation we got for the date for the EVN session. And what we got from the EV session, clear radio maps. This is like averaged observations with this clear detection of the object. However, the problem we encounter is that there was a huge thunderstorm in Effelsberg, so that we have a significant gap and huge errors in the radio observations. So we do not have like an excellent radio observations covering the same same optical observations. Based on these very preliminary results and calculations, what we can see and what is not confirming our speculation or hypothesis that there is no correlation between the optical state and radio behavior in the system, because Marcin observed the system during the quiescent or low state of the system, and we were lucky to catch the star in the high system, but still we do not see in comparison to the previous radio measurements any significant changes in the behavior. So it is rather probable that there is no correlation between the behavior and activity in optical and radio band. We will try to still investigate these signals further to see whether there is some kind of orbital phase folded, maybe coloration minutes by minute. Please remember that we managed to download and investigate preliminary these results only a week ago. And probably we will apply for another EVN session for this star to catch it one more time in a high state to get better data, especially with the Effelsberg antenna. But what you have to remember, probably right now this star will not be observed by test satellites, so that's why probably I will be asking you to monitor this star very thoroughly when we get this 1 day of observations in EVN session. This is all for me now, so stay tuned. I will probably be continuing, and also I would like you invite for the talks of our students. Mateusz, Piotr, and Badara will be talk about one object from the big campaign here about ZTF, and a little bit more about the photometric cataclysmic variables. Thank you very much.
Perfectly to time.
Thank you.
Do we have questions?
Is there any type of, the same type of any other objects of similar type that was observed, like simultaneous researchers? Not yet, but we are planning to do so.
I wanted to ask if this lack of correlated behavior is telling us something about the radio.
I think probably so, because we were thinking that maybe some high state behavior is correlated also with radio emission, but based on what we see, there is none. So probably this high state are related only due to accretion rate and not related to the radio emission.
And where is the emission coming from?
This we don't know yet.
It's still emission?
Yes.
Okay.
To answer that, probably in the vicinity of the coronal loops of the secondary star.
Yeah.
Okay. Far from the way.
Yeah.
Okay.
Okay. Thank you.
No questions online.
I don't see it.
No, nothing.
Okay.
There.
Nothing popped up.
Thank you, Caroline.
Thank you.
I will repeat this by voice as well. I said that people online want to ask a question. It's much better to go for Slack instead of Zoom chat, because this is something what we cannot see because my laptop is being taken away from me. But Slack is there, and there are people checking Slack regularly, I believe. So, yes. Good.
So I think we've lost a speaker, if I'm correct. And so
Yes.
Michelle, you are up next.
No, sorry, wait. It's coming. There it is.
So we're stepping outside the galaxy. Michelle, I think you have 25 minutes.
Yes.
So I'll give you a warning when there are 5 minutes left.
Hopefully
So let's kind of wrap up and get ready for questions.
Does it work?
I can use the arrows here.
You can use the arrows as well.
Thank you,
Michelle.
Yes.
Take it away.
Thank you very much for inviting me. It's indeed the 10 years anniversary, and it's 10 years that with my collaborator Sergio Cursimo at the knot in La Palma, we are working on following Gaia alerts. So initially, we were working with archive spectra at the time when the alerts were less well defined than they are now, and that's until the end of 2018. And in addition, we have also explored the list of objects that Susanna Kostozeva has published in 2018, which is a one-year testing period where the selection of Gaia alerts was made in a different way that Simon had designed, and unfortunately could not be implemented for the general Gaia alert stream because it seems to be more efficient than the one which is generally used. So in total, we have followed 6,300 Gaia alerts and 482 galactic nuclear transients from this Kostozeva sample, compared with LAMOST data, SDSS data, and the spectral range of LAMOST is what is indicated here. It's a relatively high resolution, spectral resolution, and that's why they don't go deeper than 18th magnitude, so it's not the most appropriate instrument. The spectral date is usually different from the alert date, which is the general case with the alerts. So we have only 2 supernovae, which I show you in the next slide. But globally, we have identified 20 cataclysmic variables, 200 galaxies, 100 quasars, among which 10 changing loop quasars. And that has been published in 2020 with the Chinese postdoc Wu Zizhu. Just to show you the 2 supernovae, on the left is one from Gaia transient. It's a 1A plus 15 days. You have the 2 spectra on the top and the subtraction at the bottom. And the other one on the right is Gaia 17A. And of course, most generally it's a 1A supernova because they're more luminous than the others. So usually you detect more 1As, although physically speaking, you have more type 2 supernova in the universe than 1As. But okay, when the alerts became more routine and better identified what the candidate could be, we could not follow all of them, so we have switched to AGN follow-up, concentrating and getting new spectra, either those which were identified as candidates or those which were variations in already known AGNs. And that was done essentially with the not optical telescope for the second epoch spectrum compared to SDSS DR16 first epoch spectrum. Now, the question there is, the selection is crucial because until the end of 22, which is the last line of my slide, we had about 25,000 alerts, and among those, 1,550 AGN or AGN candidates. And of course, we could not do all of them, unfortunately, because not enough telescope time, as you know the problem. So first, confirming those which were noted as AGN candidates in the alerts, we are strongly relying on the comments which are in the alert, but clearly I think that depends on whom is on duty, because we cannot make statistics because the selection effect is uncontrolled. You know? So out of the 429 candidates which were in the Gaia alerts, we could obtain 60 confirmation spectra, and I must say we have a bit improved our selection by looking whether the object was also detected in X-rays in the X-ray available sample, and in particular the SWIFT long-term database. And we had among the 60, 37 had an X-ray counterpart, which increases the likelihood that it is an AGN. So we have a bit cheated. Instead of going blindly, we have improved our selection effort. Now I will talk in a second about the Gaia, which you probably know, which is the paper which appeared earlier this year where people have used the BPRP spectra finally calibrated to identify quasar candidates. But the accuracy, of course, of that is much lower than what you can get with ground-based spectroscopy. So, give you one example here. This is Gaia 21CRX. And this one is not in Gaia. That's interesting. Why was it not? Probably because it's too close, and so it appeared as a galaxy and not as a point-like object, and that's probably why it was not in the Gaia. Then we have done the same on other objects, some which were not mentioned as candidate quasars in the Gaia alert, but were mentioned as a galaxy which had both GALEX, that is UV data, and WISE, that is infrared data. And we have added the X-ray data, so it improves the likelihood that the object is in fact a quasar. So the rest is the same, I have already said. And here is an example, which one is this? 20 EGA. And this one is in Gaia, and the redshift is very in agreement with the one we determined by spectroscopy. I will show you another example in the next one where I insist on the comment on Gaia. This is this one. So the amplitude from Gaia is much smaller, but nevertheless, 22 AFL is a good quasar, where you see on the right-hand side H beta, and on the left, the big line is magnesium 2. And here is the redshift we have, 0.8, and Gaia is that's generally what I quote. You see the incredible number of points after the decimal, while the uncertainty is 0.1. So it's crazy to give so many numbers when the accuracy is so poor. So clearly there has been no human waiting after the selection made by the machine, because none of you would dare to publish a redshift like that with so many decimals when the error was 0.1. But okay. So, okay. Now, the variety of QSO and AGN changes. Here you have some objects which are all confirmed quasars with high amplitude variations. It's likely that the one on the left is rather a kind of blazar change in accretion. And then you have others which have smoother variations like those, and that, okay, is a long-term trend, and we have to find out what is changing. And to give you the result already, there are two possibilities. Either it's a change in the accretion rate, which changes the central luminosity, or it may be a change in the obscuration in front of the central nucleus. To do that, you need long-term variability, and that's good for Gaia, because as soon as they detect something, they give you the full light curve, including the points before, which is very important. ZTF is not doing that. When ZTF produces a candidate, they give you 2 weeks of data, and that's not enough for AGN. And you have to do it manually to get back the data from before, which are somewhere in the database, but it's time-consuming. So it's very good that Gaia gives the full light curve. Flares like that, we don't know what it is. It's sometimes not unique. On the left, you have 1 point. On the right, you see there were several flares before Gaia alerted. But because we have no spectroscopy simultaneously, we cannot tell what it is at the moment. So you have other long-term variations. On the top, you see a smooth increasing, and then we hope it will decrease at some point. Or at the bottom, you have decreasing ones and increasing again. I must say that again, we have a selection bias in our follow-up, because you see the magnitudes are 18, 19, and of course with 2 meter class telescope, you can only do brighter objects, so we have a tendency of observing objects which are increasing in brightness and not decreasing. So again, the statistics is biased from this point of view. So what do we have as a variety in QSO change? Flares, I showed you already. Supernovae, sometimes it's not included, especially in type 2 sieverts, because we know type 2 sieverts have also star formation. We have tidal disruption events. We have found a dozen up to now. One example is here. I will show it later. We have a few extreme coronal line emitters. These are the ones which show strong lines from iron 10, iron 13, or argon 7, and so on. But they are rare. Maybe 1 or 2 microlensing events. We have not identified securely one, although Graham in the CRTS sample says he has a lot, but we have not. And so the question may be, moving dust blobs in front of the central nucleus. I will come back to that later. And of course, you need spectroscopy. And I insist also on the X-rays, because if you have a change in obscuration, you should see the change in the X-ray absorbing column density. That's why optical is not enough to distinguish. Although I show you one of the extreme corner line emitting spectrum. This one is 20 ALJ. Okay, tidal disruption event. You know that the principle is that you have a star which is passing in front of the nucleus and is disrupted by the black hole. The people are working on that say statistically you find that better in narrow line Seyfert-1s than in normal quasar, but that's understandable because narrow line Seyfert-1s have a smaller black hole mass, therefore the horizon is much smaller, and you see the event. When the black hole mass is too large, the star is disrupted, but inside the horizon, and the light is not coming out, you don't see them. Okay. And we have a dozen in Gaia alerts. Typically, they are recognized by here you have a typical spectrum of several of them. The arrow shows the complex helium-2 4686, nitrogen-2 4640, which is typical characteristic of a tidal disruption event. So here is a light curve of one of those, sharp rays, and a decay power minus 530. And an interpretation is multi-wavelength emitters there. Forget about the big blob on the right, which is the radio emitters. It's not necessarily occurring in every tidal disruption event, but you have the UV X-ray from the accretion disk, then the optical from 10 radii outside, and the mid-infrared coming from the dust. So generally, you need a multi-wavelength observation to interpret it. I'm showing you one peculiar case which we don't know what it is. Is it a supernova or tidal disruption event? It's Gaia 17 CFF. It was discovered first by Atlas as a 2070 FRO, and later Gaia discovered it in September. It was first classified as a supernova by Assas Supernovae, but once they got the spectrum, they found that the absolute magnitude is minus 23, which is too much for a supernova, but it's typical for an AGN. And a Floyd spectrum, which was obtained immediately after discovery, showed, they claimed a supernova, but in fact it was not. And if you see here the light curve, it's again a typical tidal disruption event light curve, although the scatter is very small. You have rare events like this one. And now, with time passing, you see there's a second eruption or something a bit later, but there's only one point, so we cannot say exactly what it is, because it's stay half a magnitude. So there's log there above. Yes, also, but you see a peak in 2020. Okay. So the spectrum obtained by Floyd was that, okay, this typical H alpha, H beta, H gamma. And we obtained the second epoch spectrum, but much later, after the event, and then it's clearly a narrow line Seyfert 1, where in addition to H alpha and H beta, you see the plots here, which are typical of narrow line Seyfert 1. So what was the event here? Probably a tidal disruption event, but we cannot confirm it from the available data. So a few examples of changing loop quasars. This one, Gaia said 1.5 magnitude rays in Seyfert-1 galaxy. This is the Sloan archival spectrum, and the one we obtained later shows clearly an increase of the broad lines and an increase of the blue continuum. Other example, this one, in general, we got about 300 new spectra of quasars, 51 secure changing loop quasars, 31 probable ones where the change is apparent, but we have to measure it to be sure that the change is significant. And in the Kostrzewa sample, we have 11 changing loop quasar and 6 probable ones. And as I said, because of the selection effect, we have always seen broad lines appearing and blue continuum increasing, but we have few examples of the decreasing, although we are following now some of them in the hope that they would decrease again at some point. Now, the difficult selection effect. This is one object on the Gaia light curve. When we saw that, say, oh, okay, we will take it because it seems to go down again. Yeah, well, bad luck. It stays up there. Okay. Other example. That's an interesting example. It cannot be microlensing event. Also, it must be an obstacle because it's quite symmetric. It must be possibly a dust blob which is passing in front of the object and disappearing again. But then when you look at the long term, maybe it's a binary quasar, you know? We have to get some more spectra. So how do we interpret all that? You know, the unified model says that you have, that the difference between a type 1 or a type 2 depends on the viewing angle. This is the schematics. It's supposed to show regular objects on the top and regular white objects on the top. But that's wrong because regular white you do not have a vertical. That's why it was but the rest is the same. You have the torus, which is obscuring the central AGN. If you are viewing this way, you don't see the central AGN, you see type 2. If you are viewing this way, you see directly to the center, and you see the broad lines, and it is a type 1. And clearly, if you, in our spectra you see changing from type 2 to type 1 or reverse, it cannot be due to a change in orientation, because that is not changing at time scales or even years. You know? The observer is not moving around the quasar at such a speed. So it puts a challenge on the classical compact torus model, because changes from 1 to 2 cannot be explained with a compact torus. So either you have holes in the torus, which are moving, or you have changes in the accretion rate. And so, or something else in the structure. So in practice, here is again the schematics. We need a rapid follow-up. I will explain to you why, where rapid means a few days, you know. And we have to measure the time scale of changes between the optic and the X-rays. Because if the change is due to a change in luminosity of the central engine, for whatever reason, you know, fuel flow, time disruption event or something, when the luminosity changes, the luminosity needs some time to propagate from the central object to the broadline region, which is a few 10 days light travel time. So between a change in the luminosity and the appearance of the broad lines, you have a time delay which is, say, few days, 10 days, depends on the mass of the central black hole. The problem is that with the Gaia alerts, the alert is coming often months after the change started, and so it's too late to measure this, and that's why we are now concentrating on the way when it's going down, because the problem is the same, the reverse. And of course, you need also the measurement of the X-rays to see if there is a change in obscuration. Here is just a quick calculation. What is the time change of a broadline cloud crossing across the line of sight? It's an order of a few, say, 100 days, which is compatible with what we see. If it's something of a dust blob, which is further out, it gives years, which is not compatible with the time scales we see. In fact, we need a better dust structure model, and of course, as I told you, need to measure the propagation time from the black hole to the broadline region. Now, I will show you a few similar examples to finish. As I said, that's not possible. Now, models of close by AGN, few Cephers NGC galaxies, which have been measured both in X-ray, in infrared, and in optical, have shown that it's not a single structure like the Padovani model, which can apply to those objects, you need a multi-wavelength follow-up where the infrared is measuring the dust, X-ray also, and the optical analysis. And you see, on the right side, there are 4 different structures which were derived from these measures of the close by Seyfert galaxies. And for instance, if you have a structure like this one, where the gas and the dust is completely homogeneous, nothing can change. But if the gas is clumpy, gray little blobs, or the dust is clumpy, brown little dots, they are moving around, and from time to time you can have a hole to see through the center, and then it closes again when another blob is passing before. So clearly dust models of that kind, that is not compact, but blobby structure, can eventually explain the changes we see. But on the other hand, many people think it's not a change in obscuration, but it's a change in the accretion rate on the central object, which changes the luminosity. So we have to disentangle these 2 possibilities. Okay, so I'm going quickly over that. Examples where to show that light curve is not enough to decide. For instance, here is a Seyfert 2 galaxy, which the broad lines are appearing. Another example where it was a liner at the beginning, and then you see the broad lines appearing and the blue continuum. Well, I have many examples like that. Of course, to follow up, you need at least 2 meter telescopes to get spectroscopy. Larger ones is even better, but the 1 meter is not enough to do spectroscopy of 18th, 19th magnitude objects. We have classified some older objects. I show this one 16 BPI because it's the only case where the comment from Gaia Alert was wrong. So, you know, you're quite successful in Japan. And that was a BE star. Okay. See, that's okay. This has nothing to do with AGN. It's fast blue optical transients, which are rising and going down in a few days. But one object which was thought to be that kind, in fact, was something else. 2022 CMC, it's not a Gaia alert, it's a ZTF alert, but when the object was studied, it showed that it was a galaxy, and it showed AGN structure and spectrum, which means that the AGN was dormant. So you had no sign that the AGN was in the center of the galaxy, and it waked up once the star passed too close and the fuel was brought to the AGN again. And so these variations are very interesting to find out the intermediate mass black holes. You know, we know black holes of 10 to the 6, 10 to the 10 solar masses. We know black holes of stellar origin, 10, 50, 100 solar masses, but nothing in between. And maybe these variations are the way to find intermediate mass black holes. Okay. So follow-up, as I said, we need 2 meter class telescopes. There are many in the OPTICON-ORP network. I make a little publicity for our own Haute-Provence telescope, which has a new spectrograph now. Those interested, you can apply either through French collaboration or through the ORP program. And as I hope I convinced you that optical is not enough, you need also X-ray. I make a second announcement for the SWAM satellite, which is a French-Chinese satellite which was launched in June, Space Variable Object Monitor. It's a bit like SWIFT. It has a GRM, there's a gamma ray burst monitor. Eclair is the X-ray detector. And once something is detected, the satellite is moving to the position, and then you have the small field of view X-ray MXT, and importantly, the small field of view visible telescope, which take immediately an image to see if something new has happened in that region. And then, of course, this the detection is published via GCN, and then we have to follow up with ground-based follow-up. Okay, so that's the end. Variability is an excellent tool to find new ABNs. By the way, we have done a different program in the Magellan Clouds and find a lot of quasars behind the Magellan Clouds through variability, not with Gaia, but with the ESO Vista telescope. But we need a lot of telescope time for the spectroscopic follow-up. And the reaction time depends on the type of object. For GRBs, it needs to be minutes, that's not appropriate for Gaia. Hours for supernovae, which may be marginal, but days for AGN, so there Gaia was very efficient in providing new candidates. But we still have the problem, once we have one, how do we distinguish a TDE, tidal disruption event, from AGN activity? Well, spectroscopic follow-up. I think more Gaia alerts would be welcome, but we know it's going to an end in January next year. But well, you have quite a lot of things to do already. And so I wanted to thank Simon and his team for superb work in providing legal alerts. Thank you very much.
Thank you very much. Question from Michelle.
Your light curves of the AGN flares, are those systems confirmed as AGN already, or is it just candidate AGN?
No, these were known AGNs. Yes.
Oh, no. Is it instructing how much the light curves look like CVs? Yes.
Well, there may be one case or the other which was a candidate. I don't have to check whether we have a spectrum or not. You see, we have a collaboration in the south with the ESO telescope, the PESCO collaboration. But those ones are accepting only supernovae. So when you have an object like that, they no, we cannot use it.
I was wondering why, so does all the spectra that you have, are you planning to publish them somewhere? Because I've seen some of your ATOs, and you don't publish classification spectra on TMs.
No, but we should. In fact, we are preparing a paper which should be ready by the end of this year, where we will table with all the objects and the spectra, and we can discuss if you read some in advance.
Okay, yeah, so it would be useful to have them also just to see, so that.
Yeah, so it's really useful for everybody.
Okay.
So beautiful spectrum.
Yes. And only with the 2.5 feeder telescope.
So then applying for time, how difficult is this? Because even though Gaia alerts stop, there's plenty of very long-term alerts in next year. We keep it easy on time, classify all the unclassified.
But where do you think applying for time?
To Europe instrument.
Well, in Haute-Provence, there's no problem, you know.
Okay.
No problem. Of course, the pressure is not zero. Yeah. So either you do it, and I wouldn't recommend you do this way through the OPTICON time, because Haute-Provence is very, yeah, but still there's a poll which finished just last month, and I think there may be one next year, or maybe not. Or was it the last one? It's a pity. But then you can always apply to collaboration, and I'm happy to do so. You know. But, yeah, yes. And at the Nordic Optical Telescope is the same. We have mostly done this work in empty holes in other programs or twilight.
That's perfect.
Yeah, yeah. Yes.
I find this very inspiring, and now I have a new idea I want to explore this, which is, are you ready for DR4? Because with DR4, we will have the light curves with the simultaneous BPRP
spectrum to see changes.
Calibrated. And I wonder if the BPRP spectrum will be good enough. You said with the Gaia it didn't work so well, but I wonder if BPRP are good enough to discriminate between some of these cases, because we'll have the time-resolved spectrum.
Yeah, the interesting thing would be to see if you see changes in the BPRP spectrum.
Exactly.
Yes, that's good.
Can we see change to change? The blue continuum?
The blue continuum you should see. Resolving the broadline region, I doubt.
Changes in the strength?
In the strength, yes, yes.
So I think that would be a really exciting question. Okay, if no more questions for Michelle, then we have one more talk before we have coffee. So now can you come up? Thank you, Michelle. So our final speaker of the session will be Nada Ichanek, who has 15 minutes, but little bit about that.
Good.
and take it away now. Flares, nuclear flares.
Yes, so it's almost kind of continuation to the great talk that we just heard. So I was using Gaia photometric science alerts to search flares from the centers of galaxies in general galaxies. So as we all know, we have Gaia photometric science alerts is the all sky survey, and we've been observing and producing a target since 2014. And as it was already mentioned today, right now we have more than 26,000 published alerts, and around 10% of them are flares, are extragalactic, and flares from the, not necessarily flares, but targets from the centers of galaxies. The main problem, at least that I've seen, is the fact that the definition, it's really hard to know what's the definition of a nucleus of a galaxy. Because for galaxies that are closer to us, for example, this one, it's when Gaia determines where is the center, where is the localization of the alert. In closer galaxies, you can kind of assume that, okay, this is way more centered than if it was somewhere here. In the case on the left, you can see that there's a galaxy, which is a blob, and then the location of the flare or the alert was here. So you cannot really know, was this a center of a galaxy, or was it just somewhere around the arms? So the nuclear alerts, I would classify them as AGNs, so or changing look AGNs, tidal disruption events, boron fluorescence flares, some new phenomena. So the reason why what we just heard before, right? There's changes in the disk torus, and then unfortunately we also have supernova, which are close to the nucleus of the center. However, they're not connected to the accretion or to the supermassive black hole, so they are not really nuclear transients, but they're big contaminations. So what I've done is I've done statistical study on the full set of Gaia photometric science alerts. The last time I've done this was in October last year. So in that time, there was 23,639 alerts. So I've done some cuts to try to find flares. So the first one, the main one, was a pre-classification. So if spectrum already existed from before, I kept AGNs, quasars, galaxies, as you can see, TDs, and then everything that was not classified. That gave me almost 18,000 alerts. Then I also cut all of the alerts that happened in our galaxy, so more or less 15 degrees plus and minus from galactic longitude, which was 10,000 alerts. And then based on the comments, so if there was, instead candidate supernova, it was gone. It was flare from the star or young stellar objects, stuff like this. I discarded all of this. So, and then I had around 5,000 alerts, and I decided, because there was no other way to statistically do this, I decided to do visual inspection. So I went through all of these almost 5,000 light curves to try to find the ones that I liked. So the criteria was that it has to be in the nucleus of a galaxy, which again was biased because of what I just explained in the beginning. The second one was that there was small or no pre-flare variability, because I didn't want to include just stochastic variability of AGNs. No periodically repeating flares, because again, it can be, I would assume that that's not normal, but AGN variability. And then the flare itself, or change in the magnitude, was more than 0.5. And this gave me 3,029 suitable targets. And for this, as it was also mentioned in the previous talk, I wanted to get as many spectra as possible to try to classify them. So first, these are some examples of the targets that I chose, or the spectra that I got. So the one, for example, on the bottom, this is clear flare. So you see increase for 2 magnitudes and then decreasing in 5 years. There's either slow increase, and again, this was all, I think this is like 1 magnitude increase. The one on the top right it was again increased, but then there's some, it's not as obvious flare as the one on the left, right? But still we have change. And then here you see really like, sorry, I'm using the word, but the weird flashing in the light curve. What I want to mention here, this one, by the time that I did the statistical analysis, we only saw just this first part, so just rise. So if I was doing this statistical analysis today, this one would not be in my sample. So that's why it was kind of biased, it's always biased at the time I was doing it. And all of this data, what the light curves I'm showing, this I've taken from Black Hole Tom, which is really useful for my research. It was really useful because not only you see full light curve for Gaia, Black Hole Tom also grabs the full ZTF data releases. So not just the flare, what they publish, but the everything they have. And what's even better is that we have Catalina and linear photometric observations since 2003. So I could really check the whole, the last, 20 years of photometric evolution, and the infrared observations from nearby. So up until now, for now, we have 18.6 spectra out of those 300. Some of them have pre-existing SDSS spectrum, which is really great because we are able to see how much the spectrum changed in the last 10 years. And what I was focused on the analysis was the classification. So what's the reason behind this change? The flare, distance, so redshift, brightness at the peak, total emitted energy, which must say that this is limited just for the photometric observation. So because of lack of UV, you cannot really determine full volumetric luminosity. And then from the spectrum, you can get host galaxy properties. So black hole mass, the store of stuff, I guess. So this is just half of the sample that I mentioned. So these are the data, these are all the spectra that I got from the targets of the spectra that I got with IDS spectrograph on INT, which is 2.5 meter, 4 centimeters smaller than not. But the IDS spectrograph was slightly lower quality, the resolution was worse than not, so you would be able to see the difference in the spectrum. So here I have all of the types based on the classification. Majority of the ones on the bottom are classified just as quasar, but this is because the redshift is so big that we only see the UV part of the spectrum. So without the Palmer lines, it's kind of hard to do the proper classification. In the sample, there is one changing group quasar or candidate changing group quasar, then just some increase in blue continuum. I have three candidate boron fluorescence flares and one candidate tidal reception event. One thing that I want to mention, these black hole masses are preliminary because, and they do have quite big error bars due to the resolution of the spectrograph. So some examples, the ones that are at least for me the most interesting. So Gaia 19 BZP. So there was 2 magnitude rise in the 2 months. And then it's been declining and still ongoing for 4.5 years. That's right. So the spectrum was obtained in May, so the line shows the time. And as you can see here, we have the H beta, gamma, and then the important part, the helium-2 and nitrogen-3. So these are typical lines. Also, the nitrogen-3 here is the reason why I classify this one as one candidate boron fluorescence flare and not a tidal reception event due to the nitrogen. The next one, we have Gaia 22 AFT. So the light curve, you see, again, really no variability for 10 years, and then 1 magnitude flare. We have peak around 6 months, and then it started declining, and it's still not in the baseline, but we are almost back to the galaxy. The spectrum is a little noisy, and you see here the broad spectrum line here around the nitrogen 3 and helium lines. So based on this, it's a candidate tidal disruption line. Also, based on the color, it did get bluer and brighter, which is another strong reasoning for TDM. Then Gaia 21FSA. This one is a peculiar case, I would say. So there was a pre-existing, the archival spectrum of the galaxy from SDSS. The spectrum was obtained, I forgot to put a line here, so around here in 2008. There is fairly symmetric, no, yeah, symmetric, sorry, fairly symmetric increase and then decrease. And if you check the archival data from Catalina and Linar, there's also, it can either be as a noise, but if you know that you're searching for the similar shape, you can kind of see it here. And when we check the spectra, the flux is not properly calibrated here, I think, so I need to recheck this. But when you do the normalization, so continuous subtraction, you see that they're identical. There is some increase in the Balmer lines, but there's no other change. So this could be, maybe it could be a lensing effect, or it could be binary black hole, supermassive black hole that's doing weird accretion and lensing. And then this one, it's the furthest one in the sample that we have. So it's a redshift 1.77. As I said before, we see just the UV part of the spectrum because it's so redshifted, right? And this could be potential tidal disruption event, but this is really far stretched because the reason for this, the claim is that you do see that there is not only that there is increase in the flux, but also there in SDSS, which is blue, there's no, it's more or less flat, which is typical for AGNs. And in case of the blue one, which is so around the peak, you do see the decline. So one could, we need to check this. It ideally get the spectrum of infrared spectrum to see the lines, but basically it could be potentially indicate that this is a tidal disruption line. But again, like I said, candidates. So some on the future work and the conclusions for this is that we did get in March this year 45 spectra with NTT, and there are 4 possible TDs and fluorescence flares, but the future analysis is needed for this. And in March next year, we have 3 more nights on NTT for around approximately 40 spectra again. And as a conclusion, I want to say that there were still 2 or 3 supernovas detected in this sample, so they're really contaminating, even though spectra were obtained at really later epochs. There's a variety of different mechanisms that is potentially driving these flares, and a lot of it is still not understood, so more observation, spectroscopy is needed to conclude this. And just to finish for hopefully 2 minutes, I want to, now I will switch from my science to my work, which is I'm, in addition to trying to finish my PhD, I'm also a staff observer at Isaac Newton Group of Telescopes. So I just want to show the instruments that we have. So we are currently in commissioning for the VIV, which is mounted on William Herschel telescope. So it's we have 3 modes. One is the MOS, which is multi-object spectrograph. So you have here some information on the instrument, but so we have 2 sets of plates. With one has 960 fibers, the other one 940. So we are with the resolution either 4,000 or 20,000, depending what you choose. Here it's a picture of one of the setups. So we do multi-object spectroscopy. Sorry, The second one is LIFO, Large Integral Field Unit. So the position of the fibers are here, like it's in mosaic. So there is difference between the sizes of the fibers. So most has 1.3 arc sorry, 1.3 arc second size of the fibers, and LIFO is 2.6. And the third one is mini IFO. So it's one of the MOSES can be used for this. So we have bundles of 20 fibers, which you can also position in however way you want on the on the plate. Sorry. And so for the 70% of the time is used for surveys, and 30% for open time. So everyone can apply for this. And the second one is the Isaac Newton telescope. So in June 2024, both wide field camera and IDS were stopped working. So we started refurbishment of this to put INT fully robotic for the HARPS 3. And this comes with the project which is called Terra Hunting Experiment. So for 10 years, there's going to be daily observations of 40 stars, which sun-like stars that have planets orbiting around them. So we will get extremely precise radial velocities, so to millimeters per second with precision. And 50% of the time on INT is going to be open time. So 50% is for this project, and 50% is going to be for calls. So with leaving these beautiful pictures, at least for me, this was the positioning of most fibers on the plate with the back illumination, and this is, as you maybe are familiar, the shape of La Palma, where the Roque de los Muchachos is located, and the most fiber, which is here, is the location of observatory on the map. So that's it.
Thank you very much, Nada. It's lovely to see
Oh, sorry, yeah, this is Herschel. So this is what I want to say is that if people are familiar with the Herschel, but this is the location where the VV is now, the instrument. So it was completely changed, the secondary, the primary focus. But yeah.
Thank you very much. This is slightly off topic. When does HARPS 3 start operations? Do we have a date?
So there's no official date yet, because now we're doing the refurbishment, which is going on plan, and the first flight is planned to be in next year, in 2025. But for this, we'll see, because you never know. But yeah, so far it's going we're doing everything on time. Yeah.
So questions tonight?
I'm happy to see that you are doing the conclusion. Still a lot of this and this changing.
Yes.
One comment, which I forgot to say before, and I was to use. When we compare archive spectra like slow digital survey with recent ones, one should not forget that the SDSS, the slow, has a 3 arc seconds entrance fiber, while when we do spectroscopy, we have usually 1 arc second slit. And so the comparison for borderline region doesn't change, right? But for the downline region,
it
makes
a
change. It may just be due to the change of sampling. That's why we have some objects where we are not sure that it's a changing new object because of the difference in sampling.
Yeah, I agree. Yeah. And for this, for the fluxes, we do the also flux calibration based on the photometric observations with SDSS, and then also now with the follow-up. So.
More questions tonight?
How do you determine that periodic flare went by eye?
Yeah. So this sample selection, when I was doing visual inspection, I did it by eye. So I didn't do any type of fitting. Sorry? Oh yes, I've done this many times. So I'm used to doing eyeballing. So yeah.
It's always the way that the most intriguing ones the ones that end
Yeah.
up with the lowest signal to noise.
Yeah.
Is that why they look intriguing? If they had good signal to noise, you think they wouldn't? So.
No, because they either show helium-2 or nitrogen-3, so they are clearly not quasars, not just how
So
broad line.
confidence.
Yes, yeah. But it's just that I would not want to, I would classify them as candidate tidal disruption event or candidate Bohr fluorescence flare, but to be fully confirmed, I would want to do proper follow-up, which is not really what this project was about. So yeah.
You need a bigger telescope.
Yes, and more time on spectrographs, so, which is hard to get.
Well,
But yeah.
Yeah. Any questions? Then I think we can have coffee early. Thank you very much, everyone, for keeping us. For those online and for all of us, we come back at 4:15, so we have a 40-minute break now. Thank you. I want to mute the room.
Yeah, you're here. We're here.
you very much. A little bit of hush. That's beautifully quiet. So we have 3 talks this afternoon. Yanis will be talking first on blazars and TVs, which I look to see if there's a connection. We'll find out. And you have 15 minutes, Yanis. I'll wave my hands at you when you have 5 minutes left. And
Okay.
you think about saving a few minutes for questions. Perfect. Thank you
Cool.
very much. Take it away.
Thank you. Hi, everyone. So I thought I'll just tell you a little bit about how we can study blazars entities using optical polarization, and I wanted to sort of give you a little bit of what we're doing here at the Skinnacus Observatory, but also how we can work and coordinate with different small telescopes around the world, and doing better than what a single telescope can do, obviously, and maybe convince you a little bit that adding polarization to black hole tone might not be a bad idea, although it will take some effort to work with that. So let me start by telling you a little bit about blazars. In case you're not familiar, we're talking about supermassive black holes that have a lot of gas around. They form accretion disk, and they also launch very powerful relativistic jets that we see really across the electromagnetic spectrum. And indeed, this is what a spectral energy distribution of such a blazar looks like. For some reason, the background should have been white. Yeah, so you're missing a little bit. Maybe that's the conversion. Okay. So you have to imagine there are things there too. So if I ever send you a PDF, maybe that would have been better. Okay. Sorry about that. I hope it comes out nice, but anyway. So as you see, the spectral energy distribution covers pretty much everything from radio to TV gamma rays with these 2 broad humps. I'm not going to tell you anything about the second hump, which is the high energies, but just for completeness, we think this is coming for either inverse quantum scattering of relativistic electrons or from proton synchrotron or other hadronic processes from relativistic protons. I'm going to tell you about the low energy hump, which we call it low energy, but it all goes out to X-rays, pretty much. And this is coming from synchrotron radiation from relativistic electrons that have been accelerated in the magnetic field of the jet. And one of our sort of biggest mysteries is how this acceleration takes place. So how do you give energy to particles, or enough energy to the particles to produce X-ray synchrotron? So we have 2 scenarios for that. We're either looking at shocks, and this could be shocks that are traveling down the jet, or it could be standing or recollimation shocks in the jet flow, or you're looking at magnetic reconnection, which is basically you smash magnetic field lines together, they break apart, but they cannot stay broken, right? So they will reattach themselves to the nearest field line, and if you happen to have particles there, they will give them a big boost in energy. So as you can imagine, these processes will do very different things to the underlying magnetic field, and that's why polarization is very important, because it can help us trace those changes in the magnetic field and maybe differentiate between different processes. And one neat way to do about this is with what we call rotations of the polarization angle. This is when we basically see the polarization angle going from stochastically varying to smooth monotonic changes that could be over 180 degrees. And I have 2 examples here. This is from the optical, which we have now measured a lot of different rotations there. And on the right side, I have the first X-ray polarization rotation, which was just measured earlier last year. So this is the red and blue points that you see there, where in just a few days, the polarization angle changed for close to 400 degrees. Now, here at the observatory, a few years ago, we had the program called Orbopol that basically studied a lot of different blazars, and we were, the main goal was to first detect a lot of these rotations in the optical, but also try to study and figure out where these are and how will this be produced. And we had a lot of different exciting results, but one of the sort of what we've discovered, and that was not really fully understood at the time, is that this rotation can happen very fast. And this is an example of one such rotation where basically what you see in the top panel is a change of 200 degrees happening in about 2 to 2.5 days. Right. So cadence here is very, very important because our ability to see that rotation relies on that data point. If that data point was not there, this is a big enough change because you have this 180-degree ambiguity in the polarization angle that we would have considered that this is artificial. You'll shift all the points up, they align with the other points, and then you lose the rotation. So having dense monitoring is very important. Now in the X-rays, of course, there's nothing stopping you of doing it for as long as you like, given that I give you time to do this. In the optical, whatever you do, the sun is going to come up. So it doesn't matter how densely you sample it, there's going to be gaps that then prevent you to see this rotation. So the idea, which came about this, what we call the non-stop polarization experiment, is to actually have multiple telescopes across Earth. In this case, we had 15, and we wanted, not sort of in a best effort basis, but actually coordinate campaigns where we all observe the same source at the same time. And basically, the idea is when you're looking at one location, the sun will come up, it will be dark in a different location. So in principle, you can continue observing the source more than 24 hours without any interruptions. Reality is, of course, very different than that, but that was at least the original idea. So just to give you a little bit of sense how this would work, you basically start with Japan, and then you add India, Europe, and US, and continental US and Hawaii. And you can see how you slowly sort of fill in the gaps in your light curve, and also how we see a lot of features and we see a lot of variability that we were not able to see, with a single telescope, right? We needed all the different telescopes to tell us what we were doing. And then we did not see a rotation, unfortunately, but there's still, this pretty good data set, so we wanted to at least try and compare with the different models and simulations. Now you cannot see here because the slide is dark, but the top one is for shock models and the bottom one is for magnetic reconnection ones. And it actually, when trying to do this comparison, it gets very complicated and very hard, and there's not good ways to do this because also the simulations are not exactly ready for direct comparison with the data. So we try to sort of get simple metrics that will compare between observations and the simulations. And here you see a few examples of the different histograms. So basically, polarization degree distribution, flares, the number, you see the EVPA change direction, things like that. And as you can see, there's, to our surprise, to be honest, there's a pretty good overlap in at least some of the metrics. There is not a good overlap in some others. So it's not, neither of the models can really fully describe the data, but we're getting there. I think it was very, very first, encouraging results. So now moving on to the disruption events. Again, if you're not familiar, we're talking about a star that goes very close to a black hole. It will be disrupted, and the black hole will consume its gas, and again, will form an accretion disk, and you will also see a jet form. That is not very common. We only see it about 1% of the TDEs. So our mystery here is how you would form the accretion disk. And there are two scenarios for that, or two competing scenarios at the moment. One, you have a very fast formation of the accretion disk, and then all the X-rays that come out will be reprocessed to optical and UV. And in that case, we don't really expect to see a lot of polarization in the optical, and whatever we see should be fairly stable over time. Or you have a slow formation scenario where the gas flowing around the black hole will start colliding with itself. It forms shocks. The shocks make up the outburst, and then because it shocks, we expect at least sort of higher polarization degree, and we also expect it to be more variable. So in a few years ago, in the previous Gaia Alerts workshop, I showed the figure on the top left here. This is actually came from a Gaia Alert, and You don't see the labels, but its name is AT2020 MOT, and we actually saw a very high degree of polarization of 25%, and we saw a lot of variability. And the reality again is that we don't fully understand how that happened. But we're trying to get more and more such sources, and I have two more. These are pretty much our best examples now that we have multiple observations and multiple detections. So we've made a little bit of progress, not a lot, and this is because it's actually very hard to get proposals going, and this is a very young sort of field. And in fact, in a meeting we had just the beginning of this year, I'm almost done. So you don't see a lot of the information I have here, unfortunately. But basically, this is a poster from Beagis Gonzalez, who's a postdoc here at the Institute. And this is sort of summarizing or trying to summarize the status of the field. We pretty much have about 10 TDEs that we've measured the polarization for. There may be a few more in the literature, but all of them are more than, just a couple of observations. Most of the time, these are non-detections. So we see fairly low degree of polarization, generally speaking, but the data are not really, there. So it's definitely, we cannot say that we can exclude any model at this point. So what we've been trying to do again is, instead of using one telescope, try to coordinate different telescopes. We are mostly in Europe at the moment, but we also recently were awarded VLT time. So then again, the goal will be to try and produce actual light curves of TDs in polarization instead of just a couple of detections. So in order to address both the Blazar and TDE problems, we started the Black Hole Optical Polarization Time Domain Survey. And this is an ERC-funded project, which we just started. So unfortunately, I don't have results to show you, but the idea is that we will monitor about 20 very variable blazars, and with doing intra-night monitoring, and we're also coordinating again with different telescopes across the world to do this similar NOPE-style campaigns. And we're also working with theorists in order to both improve the simulations, but also find better ways to compare the simulations to data. And also we hope that we'll get at least 5 TDs per year that will be able to actually measure get the polarization light curve from as early as possible to as late that we can possibly follow them, because we typically use small telescopes, and these are not very bright events anyway. So this was supposed to be my summary slide. So that worked out. But what it should say there is that we really need dense monitoring for blazars and dedicated polarization campaigns for TDE. So we're hoping that in the next few years we'll get both of those things with POTUS. So thank you very much.
Thank you, Yanis. I will open the floor for questions. But first, what was the Gaia TDE that you mentioned?
AT2020 MOT. MOT. MOT.
You know. Okay, any questions?
How will the Pacify survey help your science?
Oh, so the survey is not meant for transients, but we're hoping that we can hijack them and sort of, especially, so I don't know if people are not familiar with that. This is a project that aims to map the galactic magnetic fields, and there's going to be one of the telescopes here to do the North Galactic Pole, and there will be a telescope in South Africa to do the sun. So we're kind of hoping we'll hijack mostly the southern one, because here we have a polarimeter already, to follow up on a lot of the LSST alerts. But unfortunately, none of the instruments are still there. Fortunately, LSST is not there either. So, I mean, we're hoping these two things will happen roughly at the same time, so we can get maximum overlap. But that is our goal for now.
The 5 TDs that on average should happen in a year, what's for you for observing them limiting magnitudes? I mean, how faint?
So the 5 TDs per year is sort of our realistic estimate. We usually get it between 10 to 15. Yeah. We can follow up anything that is 18. If it's polarized, we can push it down to 18.5 from Skinnacus. We have not that can go slightly fainter, but this is about what we have going on now. So the 5 is basically taking into account that not everything is visible from Skinnacus, or it's happening during winter time, and it's too faint for us to follow up.
Just a comment, the polarimetric time domain data is something that we would love to have in the external.
Okay.
I started talking with people here as well, and there is some archival data as well. So this is something that we would definitely like to ingest if you have any public data.
All the rollable data for the blazars are public. I don't think the rest, because we've actually done a few different sciences. But for the blazars, we've already made those public.
Thank you very much, Yanis. Thank you. So next up is, my eyes are on your turn.
This is tight.
Hi again. Hoffbauer. Nice to meet you. Nice to meet you. And you're going to tell us about, well, I have no idea because it's ZTF, blah, 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 blah.
Yes, the ZTF and the formula.
So it's a mystery.
I hope the mystery will be resolved eventually.
So I will give you a warning after 10 minutes, and you will have 5 minutes left to get ready.
Piotr, and please stand here so that people can hear you and see you, and this is forward.
Forward, okay, and the laser is at the middle, and it goes like this, okay. Okay, hello everyone, I'm Piotr Bauer. I'm studying at Nicolaus Copernicus University in Turin. I'm currently at my 3rd year of bachelor's degree. And I'd like to talk a little bit about this ZTF object, which I hope will be my master's thesis. Many of you probably know about this object because about 2 years ago there was a huge campaign in BHM. We would like to thank you, for all of you who have uploaded the data. We do share, we have a lot of work to do. We have a lot of data. These 2 publications are my main sources of information about this object. The top publication is the original one, which is the first to mention that this object might be a supermassive black hole binary that is about to merge. And the second one is a simple optical follow-up, which adds some data in time and checks how this theory checks out. Currently, I'm trying to reproduce what's written in those publications. For now, it's a model, and I try to compare it with today's data. That's the visualization of how this binary might look like. Papers say that these 2 black holes, their masses difference can't be too extreme, but we still can point out the primary and secondary black hole. The theory says that the secondary black hole hits the accretion disk twice on its orbit. That's why the orbital period that's why period is decreasing. Yes, and that's the visualization. Here's the chart from the original publication. There's a lot of going on here, but let's take it step by step. Here we have the ZTF data. And those gray areas that are marked here are simply the peak of brightness at the moment. Here, this curve that looks like McDonald's logo in loop, is a trajectory model. In general, the minimum of a curve is minimum of curve means the closest point between the black holes, and it overlaps. They've adjusted it so the curve overlaps with the brightness peak. We have different lines. There's a solid line, there's a dashed line, and so on. Those are simply different versions of a trajectory model. For example, we can include the X-ray observations or different post-Newtonian corrections, which I will talk about in a minute. That's the second chart from the follow-up publication. They've pretty much did the same thing. Also marked those areas. Here, what's worth to mention, the original publication ends around here with the ZTF data, and it's around 1000. The follow-up publication added 200 days, and that's the zoom-in of the data. As you can see, there isn't much more data. There are like 30 points. So to talk about the good fitting of this model, I'm not so sure. We would need much more points to be able to tell that this model is correct in this time span. That's the equation that was used in the second follow-up, in the second paper, which was the follow-up. It's the edited equation of the first paper, but not that much. In general, it's a modified two-body problem with post-Newtonian corrections. And at first, when I looked at it and I had to code it, I was like, simple equation, that will be fast. Until I checked the A and B coefficients. That's A, and that's B. So after exciting retyping the whole equations to Python, there's time to go to solve this equation. So I came up with the simple initial setup where we have a main black hole in superposition and the second black hole on high eccentric orbit, and the secondary black hole is in its perihelion. That's the setup because I want as less initial parameters as possible. In this case, I only have initial velocity and initial position that I can adjust. And when I finally run the program, of course it didn't succeed for the first time, I've got this nice curve. The values you see here, I've taken from publications. Both publications weren't very specific about values they use in calculations, so it's hard to be sure if what they did is actually with those numbers. Because as you can see, this model breaks here a little bit, and that's a very interesting thing that we will discuss in a minute. I thought that if I run this model with initial parameters I found in the paper, I will get a curve that is well, I will put it on the data and it will fit. Well, if I do so, I get the model which fits with nothing. And I took the same time span that is in those publications. Here on those slides you will see BH-TOM data. That's our data. And I did the similar thing as in paper. So I've marked the brightness peaks, and they've matched with what they wrote in paper. And there are two lines. First line, the black one, is the end of data for the first publication, and the second line for the follow-up publication. So all the data behind the second line is our data, is the newest data, sorry, is the newest data. So I've tried to play a little bit with the model, trajectory model itself, and I moved it in time so it will fit with those green areas. And as you can see at the beginning, it's okay, but unfortunately, the moment we went behind the second line, the whole model breaks down. And when we look at the data, on the ZTF data, we see the constant decrease in brightness. And here, there are no longer any visible peaks in brightness. So it's a constant drop. In this filter, that's another ZTF filter that also lost its peaks in this region, but still it's decreasing. Interesting thing happens when we check other filters and, for example, Atlas. Here still everything matches, and here we have much more data points. So let's check another filter. And here we can see that, for example, here the brightness peaks might return to us, and that's the zoom in of this region. So if we are stubborn enough, we see that here and here is a brightness peak. And what I forgot to mention, the time difference between those two peaks is around 150 days. Now let's look, I need to go back, let's look at the publications. That's the region right here, and somewhere over here. The publications say that those brightness peaks should be around 20 days. So Atlas filter for now shows the best that it's not the case. What I also tried to do was to take our observations in our well-known filters. And in those filters, we can also clearly see that every filter has a drop of brightness. But if I analyze the single filter only, the resolution is not so good, so I'm not able to see those peaks. I've tried to merge those observations together, get them to the same offset, so I will get the better resolution and find out if there are many more brightness peaks. But unfortunately, if I do so, I get too much noise. I've heard that in the room and in general, there are people who know how to do it properly, because I did it by force, simple median and subtraction of values. So I look forward to talk with a person who is able to get those data on the same offset and create a chart. Oh, and also the thing with model. I've experimented with model a little bit with initial parameters, but it's very it reacts very strongly to the change of initial parameters. So I would also like to ask for help with recreating a model. And that will be it. Thank you for listening.
I'm curious, what was your assumption about the black hole spin?
Spin.
Yes.
Assumption. I can talk only about what I've read from the paper. It's hard to say. I only read about what will be spin after the collision, but I'm not able to tell you anything about the separate spins of them.
Okay. I was very skeptical. That was maybe 2 years ago when I was talking about resonance for this case, because what you see here are mostly variation from the jet. There are different cases which show this, and of course there was the object with a model, which I don't believe it's quite correct, especially in this aspect that there is a accretion disk around a smaller mass black hole. I'm not a theoretician, but I see the results. There should be no efficient list when the secondary black hole is away from the track.
There are several scenarios in those vectors, if I remember correctly, and the accretion disk is one of them. Yeah, and yes, the other one. What's interesting, when I sat and heard 3 or 2 presentations before me, the TDEs and some other things had very similar light curve, and it sounded a bit light a lamp in my head, but we'll see.
Can you go to your high resolution atlas
Uh,
yeah, that one. I don't know if my eyes are deceiving me, but in the early part it looks like there's some potentially periodic variability. Have you run it through a power spectrum, this data?
No, not yet.
I'm second is the same too.
Yeah.
But what is the error on this one? These drops are drift? Or is this
This is the real variability, so this is not the error. Yes, definitely. Okay. The first approach we did was to check try to recreate the model which were published, but what is surprising that based on what they published and presented the information about the initial parameters and equation is undoable. Also, the problem is that what we were able to do at the first attempt is that we definitely can definitely say that we cannot confirm this decreasing years to the 20 days multiplier. This is all attempts to recreate the model. So right now, I think the best solution will be to change the strategy to solve it in a different way, or I guess with a different model.
So, first of all, nice work. Thank you. But then, I guess your model, you would need to increase the sampling in your model?
Yes, that's also well done.
Large caps, and that's why we don't see it very clearly. But I assume there is still some variability which should be going on here. But that means if you extend it, can you give us a date when this is going to happen?
It's hard to say. I've stopped experimenting with the model as soon as I've noticed this atlas, because the periods we see here, they have constant time gap between them. So it turns out that this period is not decreasing, or decreases much more slowly than anticipated.
Which is a very valid discovery. It's true.
And what is the nominal scatter at such magnitude for atlas? Because I think it's not that reliable at that magnitude.
Okay.
I would guess the spread in y direction may play a viable role here as well.
Okay. I have many things to check and learn.
Thank you very much.
Thank you.
Yes, she is online. Anna should be online.
Hello?
Hello.
Can you hear me?
Yes.
We certainly can. Good.
Can you share your screen, please?
Okay. Can you see my slides?
Yes.
Yes, we can.
Okay.
Okay. Full screen, right?
Just a second. Yes,
It is full screen. We haven't made you full screen on the screen just yet. And stop recording.
Yes, because Anna requested this, and I'll also stop the YouTube. So bye.
I don't want to be on YouTube.
Right. It's okay. Let's stop.
And let's make the screen full screen.
Just a sec. I need to stop a couple of things.
Just to